Welcome to OARC 40, and for those of you in the room, welcome to Atlanta. It's nice to see that we've got about 75 people in person, and then we've got about the same again online, so this is a truly hybrid event. My name's Keith Mitchell. For those of you who haven't met me, I'm president of OARC, and before we get started, I'm just going to run you through a few informational announcements and a little bit about OARC itself. So, it's a hybrid event. A reminder to you all that there is a conduct policy which you signed up to either as an OARC member or when you registered for the workshop, and that applies to online interactions as well as in person. So generally everyone is extremely well behaved at OARC meetings, so let's keep it that way. I want everyone to have a good experience. The workshop is being recorded, and the talks will be available on the OARC YouTube channel before the next workshop. It's all Zoom webinar format, so if you're not a speaker, then you're muted during the event. Time zone, here we're 5 hours behind UTC, and general times will be in local meeting time in Atlanta. Social media, I see the slide has managed to crop them off the bottom, but the hashtags are OARC40 and LoveDNS. We haven't actually had a volunteer for doing social media this time around, so we'd strongly encourage you, if you're interested in posting stuff about the workshop, to use these hashtags, and we have a cool new toy for that as well. Okay, you probably already figured it out. Same Wi-Fi credentials as last time. The breaks, the coffee breaks, are in the foyer immediately outside. The lunch breaks are in the other half of the ballroom on the other side of the wall there. And there's restrooms on both sides, which I'm sure you'll manage to find. In the event of an emergency, there will be audible alarms, and basically you should go up the stairs to the hotel main lobby, out through the hotel main lobby front door, and there's an assembly point to the right at the end of the block, and the hotel staff will be wearing yellow vests to help guide you should that happen. Any other issues, if you're not feeling well or anything like that, then please speak to one of the OARC staff. You shouldn't have been in this room unless you already provided us with your full vaccination proof and a negative test this morning, so thank you for doing that. If at any point you test positive or are feeling unwell, then please, we recommend stay away from the meeting. Hopefully the worst of the pandemic is behind us, but we wanted to stay careful there. A few things that we encourage. We hope you all tested before you traveled. There's plenty of tests, so please test again tomorrow. We won't be checking that, but I appreciate if you do that. And there's plenty of masks, so if you feel you need to wear a mask for you or another benefit, and then by all means do so. And if you're not comfortable with these measures, then please attend online, and Dinesh and Rebecca can help if you have any health issues, concerns, or symptoms. As usual, we will be doing interaction via Mattermost chat, and the workshops community channel will be used for that, and that will be used for questions and answers, talk rating polls, timekeeping for remote speakers, and general discussion. So if you haven't signed up for that, particularly if you're online, I recommend that you do so already. There's plenty of cross-platform clients or use a browser. Questions, speaker slots each include 5 minutes of Q&A. We'll do that on a first come, first served time permitting basis. Obviously, the breaks or the online social are available if you want to attend to that. Please identify yourself and affiliation when asking. And what we're doing, as we did last time, is putting all the remote speakers into a single session. There will be a remote session chair, so that's tomorrow. And we're handling Q&A differently for each of these. For in-person questions, if you're here in person and you're asking an in-person speaker, then please queue up at the microphone line and the session chair will ask you to speak. If the speaker is online or you are online, then it's a bit different. Please use Mattermost and prepend your questions with hash questions in the workshops channel. And this is not the right slide deck version. The person who will read out your question, the thing that we're doing this time is that the remote speaker will read out your question from the Mattermost channel before answering it. For feedback, we're using real-time Mattermost polls again. Again, you will see these polls in the workshop channel. Please display this during the Q&A and talk, and please vote. And that data is really helpful for the program committee. And general event feedback is, there's also a survey for that. It's welcome. Lightning talks, we have a 30-minute slot for these tomorrow at the end of the workshop. It's always good to have late-breaking stuff. Short talks, a maximum of 10 minutes. Indico submission is open for that. Please, if you have a lightning talk you want to give, then do it by 11 a.m. Eastern tomorrow, and the PC will select and notify speakers. I also wanted to tell you, the slide seems to have got lost in a version change. I also wanted to tell you about our social media platform. We're calling it Masto DNS. And at the moment that is open to OARC board and staff and PC, and we will be opening it up more widely next week to OARC members. But if you want to try it out today or tomorrow, then let us know and we can get you signed up for that. OARC team, we have a bunch of people here in Atlanta. The whole OARC staff is here in the same place for once. I'd like to welcome our latest member of the team. You probably already met Rebecca, who was at the registration desk, who's basically our administrative coordinator. Everybody else here has staff marked on their badge. Most of the program committee are here, and we have 3 program committee members who are not able to attend in person but should be reachable online, and a couple of board members, and Joao, Joe, Ray, and Shumon are all here from the board. 2 social events. If you're attending online, we're using spatial chat again from 2110 to 2300 UTC. There's the link, and a password will be emailed out to you for that. And if you're here in person, we're having an in-person social at Metro Bar and Diner, which is just around the corner. You do need to buy a ticket for that. Social registration is still open, so if you didn't get one, there's still time to do that. And that starts at 5:30 for a couple of hours tonight. It's around the corner. I think there's a walkway path to it as well. So that's the workshop stuff. I'm just going to give you a very brief update on OARC. It's not that long since we had our AGM and our last workshop, so I'm not going to run you through a whole bunch of stuff that you probably heard already. Why are we here? We're here to make the DNS work better. We do that through research, through tools and services, but most importantly, community building, of which these workshops are a very important part. Sharing of information and knowledge, and just generally increasing knowledge and clue about the DNS in general. These are our members. We have a community of over 100, and they range from the very large to the very small, including our supporters. Committees and board, at the AGM back in October, we added 2 new board members, Joe Abley, who is now taken over as treasurer, and Shumon Huque, as an ordinary board member. Program committee this year is the same as last year with one addition, Peter, who's here today. And we also have a privacy committee that's working on overhauling our data sharing agreements and some other important work there. You probably know this already, but we cannot escape inflation, and there was a decision for the first time in several years to increase OARC's membership fees as of the 1st of January. Most of you who are up for renewal will know this already, but you know, it allows us to continue to provide the level of service to you that's important. If this is giving you budgetary difficulties, we've overhauled our multi-year discount scheme, and Steve will be very happy as membership coordinator to talk to you about that. And you know, why become an OARC member? I'm not going to overegg it. If you're not a member already, then talk to the members who are, and I'm sure you'll tell you that these are some of the benefits. And if you're not, and if you are a member, again, thank you very much for your support. Okay, that's pretty much all you'll hear from me until the end of the workshop, but I'm around if you need to talk to me about any aspects of OARC or indeed to any of the rest of the team. I will now hand you over to the session chair for this morning's session, Suzanne Woolf, and our timekeeper, Puneet.
Good morning, everyone who's here with us in Atlanta, and good day to everyone with us out in Radio Land. Welcome to OARC 40. I'm Suzanne Woolf. I'm a member of the OARC Program Committee, and I'll be moderating this morning's session. Quick reminders, Keith just went over some of the workshop logistics, but just a reminder, we'll be taking questions from the workshop's channel in the OARC Mattermost, and in the room here, there's a microphone for folks in the room. If you're putting a question in Mattermost, please start it with #questions. That makes it easier to pick out. And a poll will appear in Mattermost around the beginning of each talk. Will be active until the end of the session. This poll will be the only opportunity to rate the talks. So please do that. It really helps the PC and the speakers. A couple other notes. The call for lightning talks now open. The PC is accepting 5 or 10-minute presentations from in-person presenters for tomorrow's afternoon session 4. The CFP will close tomorrow at 11 a.m. local time. So if you've got something interesting to share that's a little timely, a little quick, please think about doing a lightning talk. Petter Spacek will be the timekeeper for this session. Thanks, Petter, for keeping us on track. We also want to offer special thanks to VeriSign for being the 2023 OARC Workshops patron. As a final administrative point, please note that OARC Memberships Manager, Steve Sullivan, is giving an on-the-spot portal training in the foyer outside the meeting room. He's giving away free drink tickets to the first 10 people who take the crash course. And the portal is useful. This is stuff you want to know. So make sure you see him to learn more. I think we're ready to get started with the first presentation. Puneet Sood will be talking about learnings from deploying cache poisoning protection. Don't forget to watch for the poll in Mattermost, and welcome, Puneet.
Okay. Hi, everyone. I hope everyone's caffeinated or awake using other substances. All right. I'm not a morning person myself, so I'll try to do a good job here. Let's see. As a reminder, so Tian Hao is the person who did most of the work, but he couldn't make it here, so I'm presenting on his behalf. Let's see if this works. Yes. This is the agenda. This is going to be short. We might even be done in less than 10 minutes. Recap what we presented at a very high level at OARC 38 in Philadelphia, and then discuss the deployment experience we've had with some of the interesting approaches. All right. Yeah. To summarize, the key takeaways from the last presentation were that cache poisoning is a risk if you do the mathematical analysis, is a risk for UDP queries. UDP is still the majority of DNS traffic, so it does matter. There were some mitigations proposed in the, I forget the RFC number, something in the 5000 series around port and query ID randomization. Then DNS cookies was proposed. Case randomization was a proposal from Paul Wixie, which didn't make it to RFC, but still lives as a draft. Google Public DNS does implement that. Unfortunately, it turns out that DNS cookies are not supported by the majority of query volume. It's supported by about 40% of the name servers, but when you look at query volume, the percentage is very low. And in addition, there's a couple more mechanisms which can be used. There's the non-prepending for TLDs, and of course, our favorite DNS over TLS, because that will solve a bunch of other problems also. Okay. I think I covered most of this. So this is summarizing the approaches we are using. All right, so in terms of the updates we have from last time when we presented in Philadelphia in July 2022, at this point, after a lot of analysis, we have enabled case randomization in a number of metros, not all. It's a significant percentage of our traffic, but not all of it. And in the metros where we have deployed, we get about 90% coverage for UDP traffic, which is very encouraging in terms of coverage. We do have servers which misbehave or don't comply with getting a response back with the case preserved. And that's been the work here in terms of making sure we are not breaking queries for user domains. It does include one large operator who we've been trying to figure out what's going on there. And the problems we've observed, the first few problems are what we mentioned earlier. The other interesting thing which we noticed was that when you probe at low query volume, it looks okay. The cache is, the case is preserved. But when you start sending queries at a high query volume, that's when you start seeing the problem. So that's very hard to detect in initial testing. We only found out as we deployed to more metros. So at the moment, we do maintain a disable list for case randomization. It's enabled by default, and we turn it off for the ones we know don't work. It's a manual process, and at the moment, yeah. So, hold on one second. Yeah, okay. The thing to point out here is at the moment there are about 2,000 name servers for which we have to disable out of a total list of around more than 1 million. So we have the disable list which is manually maintained, and the primary fallback is to go back to TCP. The worst case scenario there is that someone deploys a new version of their software and then it completely breaks case randomization. To be able to deal with that, we are actively looking at some more intelligent fallback mechanism that if the signal is that it's completely broken, to automatically turn it off. We don't have to depend on humans for that. Okay. I think this is the one, DNS cookies will be the more interesting one to discuss. We have at the moment not enabled automated DNS cookies for all traffic. We manually enabled it for more TLDs. I think .uk was one of those which we have enabled. There's probably a few more. Thanks. And we have enabled probing as part of our production service to get better metrics on DNS cookies. And with that, the expectation is that we'll be able to cover about 12% of query volume. So it's not very encouraging that way. And here's the list of different kinds of responses we get. Failures, encouragingly, is less than 3%. Complete failure where the server fails to respond or generates a very unusual response. However, the total coverage is still much lower than we would like. And we noticed interesting behavior in the bind and not implementations, which is mentioned here, that those two resolver implementations don't consider a server which just echoes the client cookie as sufficient for confirming the validity of the response, while we think we may be able to use it for that purpose. And in terms of mitigation, again, the same approach that we will fall back to TCP. Here we do, given that we are able to cover a small amount of traffic and it's manually configured, we do, if we see consistently that cookies don't work, we will turn it off for that name server. Okay, so this is the adoption rate for cookies as observed from our probes. As you can see, the amount of name servers which support server cookies has gone up slightly. However, the query volume hasn't really moved much. So this is the part where I guess the question becomes what's holding back name servers from doing it, especially large operators which handle the majority of the query volume. So it turns out, meaning I think at this point all large open source implementations do support it. So, and the RFC section 7 also covers the topic of incremental deployment. So it's not completely clear why it's not being turned on. one of the hypotheses we have from reviewing our own server implementation is that rolling out when you are running DNS behind an Anycast IP, which is served from multiple metros, and even within a metro served by a large number of servers behind some load balancers, that the slow rollout may cause issues for clients which are tracking cookie support at an IP level. Maybe that's the concern. That's something we are evaluating for our own service. I don't know about others. We'll be curious to hear. Okay, and some ideas about what could be done. And for authoritative DNS over TLS, not much has changed since last July, except that I think more servers support it now, and we have gained more experience. And thank you to, I think, the large operators who have enabled it. Some of them are listed here. DOT looks fine at a high level. There are some issues with connection management. One set of issues we noticed is that some implementations just close the connection earlier than we would think. Either they'll close it on a fixed time value, or they'll close it when we send the next query to them. So which leaves the in-flight queries failing, which requires then on the recursive side to implement some ways to retry the queries, which we weren't expecting to have to do. And then there's a problem specific to our resolver implementation, which has to do with the fact that since we run a large number of servers and the outbound queries are also load balanced, that the connection count is higher than we would like for some mid-size operators. All right. Okay. So for DNS cookies, these are our plans. I think given time is almost running out, I'll not talk to each point, but we do plan to, if we can figure out the compliance issues with DNS cookies, we will probably move forward with auto-enabling it, but we are not sure. Auth DOT, we are primarily looking to do better scaling there so that we don't leave too many connections open. All right. Thank you.
Ralf Akamai, thank you for the talk. Well, one remark and one question. So one remark on DNS cookies. I still think it's not a good idea. And there are things down the horizon with DOQ that are much more better suited to kind of having, and solve more problems down the road. So that's on DNS cookies. On the OX20 stuff, do you actually have plans to publish the list so that other operators could use them?
I think we'll have to run it by legal at Google. Meaning, I would love to, but I think there's both a question of, it's not about blame, name and shame kind of thing, it's more to improve. So we have to basically get over that hurdle to see if we can share some information.
Yeah, I mean, the problem is OX20 is implemented in lots of other stuff, but nobody's actually using it because of those servers that are kind of responding bad. So if you would have a list, you might have get better adoption there.
Yeah, I see the point. I think it's a matter of process to figure out if we can do it.
Thanks.
But yes, yeah.
All right, we have a question from the workshop channel. Brett is asking, well, more a comment. While enabling cookies for TLD auth in my previous company, we encountered some issues with F5 load balancers supporting cookies, which as far as I know is waiting for a fix from F5. So if anybody else has a comment or if that's a good caution. Thanks, Brett.
Thanks for the update. So I guess we can look forward to more cookie support. Yeah.
Anybody else with a question in the room or online? Going.
I think there's one last one there.
Hey, this is Matt from AWS. I noticed that you disabled PTR support for your case randomization, and I was curious why that record type explicitly.
We covered it a bit in the previous slides, but the point is that some servers, when you probe for the non-PTR records, they happily support X20, but when you send them a PTR query, they don't preserve the case. I just assume it's special code which doesn't do the same thing.
Got it. Thank you.
Yeah. All right. Thanks, everyone.
Thank you very much, Puneet. And Andrew, if you're ready to go. Andrew Fregly is up next and will present on a research agenda for post-quantum DNSSEC, which I'm really interested to see. I'm glad we have that. Thank you.
Hello, everybody. Hey, I appreciate your time and attention today. I'll start by saying this talk I'm preaching to the choir here, and you guys are the ones who do the research on DNS and DNSSEC. But still, I think this will put together a little more comprehensive view of maybe where we might go. So one thing is, why would we even have a research agenda at this point in time? Well, the people have speculated, or research has indicated, surveys, that quantum computers, the earliest that there might be a good likelihood is 15 years from now. Some research or analysis says it could be 50 years or more. It's kind of like nuclear fusion. It's one of those deadlines that keeps moving back at calendar time. But still, I want to point out that regardless of that, the standards activities are going forward. NIST has selected the first set of post-quantum algorithms. And in the US, the National Security Agency has said that all the critical defense systems by 2033 need to shift over to the post-quantum algorithms. So regardless of when the computers show up, the algorithms are going to show up. By the way, at VeriSign, I'm a principal engineer reporting to Bert Kaliski, our CTO. I'm sure most of you know Bert. Next slide. Oh, I got it. I have the power. Okay. So, like I said, in addition to the factors that the standards are coming, what are some of the things that we might want to research? Well, we need resiliency in the DNSSEC ecosystem. Having a single algorithm family, or even two algorithm families, puts the ecosystem at risk. And this is a long history of cryptographic algorithms getting broken. In the NIST competition, 2 of the 4 major algorithm families got broken during their lead up to selection. And these are new algorithms, having out multiple algorithms ready to roll out for DNSSEC is critical. Second reason for this, as I'm sure you're all familiar, is these algorithms have big signatures. Some of them have big keys, but it's really the signature sizes. And why does that matter? I'll talk about that a little more in a minute. So we have these issues that these large signatures primarily are going to present to DNSSEC. So say, well, if we know what the issues are, what are some of the solution approaches we can have? So the solution approach is, you'd like them not to have any impact on the current operation of DNS and DNSSEC, but it's very likely that we might need protocol changes or some adaptation to these larger signatures that these algorithms produce. I'll talk about that a little. And then when you look at this, like I said, this is the preeminent group here for studying DNS and DNSSEC. But given the sheer magnitude of change this might incur on the entire DNS ecosystem, we need a complete view. And I don't know if any single entity right now can assess from stub to resolver to authoritative, all the networking infrastructure, what the impact of potential protocol changes might be. So that's where a collaborative, multi-stakeholder approach is needed. Well, so let's start looking and one of the primary issues that the size of these new algorithms presents to the UDP transport that's prevalent for DNS. So if you look at that bar there where it says DNS over UDP limitations, the darker green represents the 512 byte UDP MTU that was prevalent ever since DNS first started. You get into the lighter green, now you're at the area where RFC 4035 says a minimum UDP MTU for IPv6 should be 1220 bytes, and in practice it's typically around 1232 bytes. When you get in the orange, that's where RFC 4035 says you can go up to 4096 bytes, but we don't really know. It's not uncommon to use large UDP packet sizes at that level, and we don't know what the impact would be if we were to try and use larger or enforce larger UDP MTUs. When you get into the orange area, that's just unspecified. We don't know if there's any support for that. Now let's look below that where we list the algorithms. The first three, Crystal's dilithium, Falcon 512, and Sphinx 128, those are the algorithms that NIST selected in their recent algorithm selection process. And the bars indicate the signature sizes of those algorithms. Now you'll notice that all those three algorithms, all of them are over that past the green area, which is where we're pretty sure it'll work over UDP right now. And even Falcon 512 with the 688 bytes, if you look at INSEC and INSEC3 responses, you're going to have multiple signatures in them, and you'll be over that UDP max. The other two algorithms are stateful hash-based signature algorithms. Little known secret that stateful hash-based signatures, as specified in NIST SP 800-208, are approved post-quantum algorithms. People shy away from them for use cases like DNSSEC because they require state management. But still, they could be considered in certain circumstances. Then below at the very bottom, we have an elliptic curve algorithm. They both have this, Edwards and the traditional, both have small signatures. And RSA, of course, has a little bit bigger signature. And it fits well within the UDP MTUs, even if we're doing multiple signatures. So that's the problem. If we want to maintain UDP as a transport, it's a critical issue to address. Another thing I haven't seen much discussion on is what does the footprint of these new algorithms will be on your authoritative name servers that use in-memory databases and on your resolvers that have in-memory caches. Now, a lot of the performance that we expect out of DNS is due to putting these things in memory. If you have to go off disk, and if it's fast disk, it's going to slow things down. So if we look at these different algorithms on the green bars, which is the horizontal chart, we're really tracking, how much of the zone would be comprised just of signature data, not even the wrapper around an RRSig, just the signature data. So if you look at elliptic curve, if the zone was fully sized, and by the way, I'm looking at TLDs where about 2.2 RRs per RR set, and you're signing all of them. With the elliptic, you'd be almost 40% of your zone. I'm looking at the zone file, not the in-memory database, would be signatures. If you go to RSA, you're over 60%. By the time you look at Falcon, you're well into your 80% range. And when you get to Sphinx Plus, you're at 99% of your 99% of your zone file signatures. This is what my boss Bert calls the tail wagging the dog. But we want to authenticate our responses, so we have to deal with this. Now on the bottom graph, you see in the orange, that's the elliptic curve plot as a percentage. We're comparing basically the other algorithms to how much growth would there be in the zone file if we went to these new algorithms, went to Sphinx Plus. So you can see if we were going from an elliptic curve to Sphinx Plus, you'd have a 5,000% increase in your zone file size. If you went from RSA, you'd be around 35%. So 3,500%, 35 times. So that, so in many applications, and I think maybe the Google guys can empathize with VeriSign, you know, that might be an impact. So let's talk about a few approaches. And by the way, if any of you, we're open to all the suggested people can for approaches to deal with it. We only have one caveat. It has to start with the letter S, okay? Does everybody get that? So we have smaller, selective, shift, skip, and split. And I'll just briefly cover each one. So smaller, how can we make these, you know, you got these large PQC signature algorithms. So there's one approach would be, let's find a smaller signature algorithm. Well, NIST actually has another selection process they've just spun up to try and look for an alternative signature algorithm. There's no guarantee they'll find one, even find one, much less find one with smaller signatures. The other one we have is something we've developed at VeriSign, building on other people's work, and that's what we call a Merkle tree ladder mode. And I'll talk about that in a few minutes. I got 10 minutes? Okay. And then we have selective. This is something actually Shumon was one of the authors of a draft back in 2013, where you can, it doesn't solve the problem, but it lessens the problem by, let's say you're doing an algorithm rollover, only give me the latest algorithm. Or if you're in a hybrid situation or you're using multiple algorithms assigned during a transition, just give me the algorithm I want. Shift, let's change how we get the signatures. So in that, we might do out-of-band retrieval, you know, like push this data out through some other mechanism to the resolvers, or use a stateful transport to interact with the servers. But that has repercussions. And skip, that's a mechanism we've looked at a little, where what could you do to do proactive caching? It kind of goes hand in hand with the shift. Can you actually get these ahead of time so you're not trying to do them in real time, and use a transport that's better suited for that? And split, I was talking to Douglas Stabilo last fall, and he said his master's student, Jason Gertson, was working on this cool project, and I don't know how viable it is, but his idea, which he presented on at PQNet, was let's just break the responses down into separate DNS records, and then the stub or the resolver asks for them one piece at a time. He set each piece size so they'll actually fit. So, like I said, if you come up with more, just make sure it starts with an S. Now let's look at Merkle tree ladder mode. This is something we've worked on. I'll briefly describe it. So the concept here is you still have your traditional ZSK, but the ZSK doesn't sign the RR sets. What it does is it signs the root of one or more Merkle trees. That, and the Merkle trees basically are used to authenticate your RR sets. So your RR sets become hashed, and then those hashes become leaves in a Merkle tree, and the roots of the Merkle trees are reference values. Well, you can authenticate those data elements are part of fed into the Merkle tree through standard Merkle tree authentication paths. Then you just have to authenticate the root of the Merkle tree, and those are signed by the ZSK. So we've got, Bert's going to has spoken about this at the NIST 4th PQC standardization conference. We have a paper on this. We're going to do a paper for CTRSA in the spring, and I think a much more readable version of that paper, and a very good presentation on that Bert's going to do. So what does this do? If you use this Merkle tree approach, your authentication paths are composed of 32-byte hashes, and the number of you have is basically log n minus 1 of the number of things that you've signed. So if you're signing 20 million records, you'd have 19 hashes. They could be 32 bytes. If you're signing 10,000, it's whatever that is. And so that becomes much smaller. Now in here, we show the links on the left, and those are using the 32 bytes, which is NIST level 5 security level. If we go to NIST level 1, we're using 16-bit hashes, and those authentication paths are even smaller than what you see here. They're half the size, but you still have overhead for the signatures. And the idea is that most of the time you're retrieving these condensed signatures that are primarily composed of just the authentication paths, then you're verifying them against that signed reference value. Every now and then you need to get new reference values, and that's been part of our research, is to say, how often would you need to retrieve those reference values? And we'll cover that very well in Bert's upcoming paper. How much time I got? 5 minutes. Okay, so when we look at a research agenda, like I said, here's where I'm preaching to the choir. First thing we need to do is understand the overall DNS ecosystem, but have it'd be nice to have a single, or as much as possible, a single view of what the entire ecosystem looks like. And that goes down from your stubs to your resolvers, your authoritatives. Understand what software's out there, what hardware, what does the networks look like? Anything that has to do DNS, basically. What are the constraints on that? What are we operating under? So that's the first thing. So then you get an overall picture of what the DNS ecosystem looks like as far as software and hardware, and then you do the same thing. You look at the networking. We realize that the networking constraints vary depending on the use case. Stub to resolver is a different use case than resolver to resolver or resolver to authoritative. So we really want to understand the characteristics of what's out there and what are the constraints on that. And then we want to look at the traffic, what we have now. And as we look at that, we want to look at how well they can handle truncation and fragmentation. I know there's been a lot of research already on fragmentation or fallback to TCP and what the level of failures that is. Let's tie that all together and then use that kind of to look at the session-based protocols and the impact they might have. And then we have, and we want to do this at different levels too. Your root traffic and your root servers are very different, believe it or not, than your TLD level, and they're very different than second level. And we don't even really know much about third level, but you have different characteristics and different factors that might play into, and all this is going to feed into like your standards activities. Because what we want to do, once you've got this model and you know what's going on, well, then you start the impact, project the impact. So if we do these standards changes, someone's proposing them, instead of saying, oh, it's a good idea, it sounds like it might work, or we did this study in this environment, instead now, can we model it in such a way where we can actually project that, yeah, it's great for 95% of the DNS ecosystem, but it's going to break 5%. Well, that's not acceptable. So well, maybe it's not acceptable. So let's look at the overall impacts based on that prior research, model the impact of the PQC algorithms, model the impact of proposed protocol changes before we start putting in place standards and moving forward on the standards activities. And then, because it's going to take a long time to transition, there'll be different intermediate states, such as the use of hybrid algorithms or multiple algorithms. Different devices transition at different times. Then, can we project in the future, will we break at different points in the transition, or what would be the impact? And so we have well informed. So with that, I'm done, and I'm open to questions. Hello.
Hi there, Eric Zegast, Domain Tools, aka Farsight Security previously. And so your talk had a few thoughts roll in my head. We have a view of what is generally a recursive view of DNS. And we've always found that when we split out DNSSEC from DNS, DNS may have more, if you on a shorter time horizon, may have more data. But over time, DNSSEC continues to have more and more and more data for the same time period. when you're talking about the size of the zone file, not everyone queries everything in the zone file, but I'm curious as a research effort whether how much of the memory space of recursive name servers is being used for DNSSEC and seeing a measurement of that over time as these new algorithms get implemented or tested or whatever. I think that could become a huge problem if, you know,
Yeah, that's
if it's not considered fully, and maybe alternative ways of doing caching or such for DNSSEC outside of memory space might actually be a necessity in the future if what you're saying comes true.
and I mean, they're coming, the algorithms. So said we can only see what we send out, you know, at VeriSign. And it's hard to really know what's going on from our perspective, what's going on in the caches. That's why I say it's going to take collaborative ecosystem-wide research, because you know, I suspect that the problems of the big resolver farms are going to be even worse than the big authoritative, but I don't know. So this is why I'm asking for the collaborative research, or we're asking for it at VeriSign.
Sounds like something we would want to participate in.
Yeah, well, I'd love to talk about that further. Yes.
So we've got a question now from the remote, from the channel. Hazel Esk is asking, how about supersizing, i.e. rather than splitting a large signature across multiple RRs, how about having a signature sign a bundle of RR sets instead of one RR set per signature? You can reduce the overall cost of signatures by amortizing the cost of each sig over more records.
Well, that's kind of what we call, if you look at the Merkle tree mode that we propose in the MTL mode, if you think about it, that's exactly what it is. It's a concept of aggregation. So if you look at the reference value, the root of a Merkle tree, what it's actually doing is it's signing all the leaves. So that's kind of the whole approach we've been following with that Merkle tree ladder mode. Like I said, I can give you links to the paper we've already got out there and the talks we've done on it. And there may be other ways of doing it, which is the out-of-band retrieval stuff I've talked about. There's all types of research. Can you do prioritization or predictive analysis of what resolvers might need? Give that to them. And that stuff, you know, to me, that's part of the research effort that we're asking for.
Right, yes, thank you.
Hi, Vicki Riss from ISC. It's slightly off topic, but I know you can do this. Could you give us an update on what you think the timeline is for implementation as far as the standardization and the availability of the libraries?
Yeah, I know at VeriSign we're working to get MTL mode prototype on code that we can get for submission into CFRG. I can't give you the timeline for that, but we're working on it. So that would be an implementation of that. As for the other algorithms, there's code out there right now, you know, like the Open Quantum Safe project, which Douglas Stabila kind of runs over there at the University of Waterloo. They've got working code there. The thing is that NIST has said they won't do the final parameterizations until they publish their NIST standards in probably 2024, it could be 2025. And then we'll have a much better idea of what the exact parameterization of the algorithms will be. But there's actually working code out there that people can start to use for the NIST algorithms. And the two stateful hash-based algorithms, LMS and XMSS, you know, those have been out there for a while, and there are actually some standards that I think Russ Housley has worked on, you know, for some of the message signing that there's RFCs for those out there already. So, Vicki, to tell you the truth, my prediction, you'll see IETF standardized shortly after NIST does final parameterization. Then it's just how fast will the IETF move to standardize them, and the open source libraries, I suspect, will start to put them out very shortly after that too, but it's hard for me to project beyond that. Thanks, Shumon.
Hey, Andy, this is Shumon from Salesforce. So I think you may have answered a few of my questions already in response to Vicki, but I had a couple of questions on the Merkle tree ladder mode. I remember back from when I was at VeriSign, hearing Bert talk about it. So I'm glad to see that you guys are continuing work on that. So apart from the papers that you have published and the presentations, I was going to ask a question about writing specs and standardization. So you mentioned IETF maybe at some point in the future. I was thinking another possible venue, maybe the IRTF, to write a spec for that and present it there. So that is one suggestion for you. And I had another question about whether or not you guys have implemented any of that stuff for prototype for DNSSEC.
Yeah,
It sounds like you might be doing that in the future, right?
I appreciate it, and I think our intention right now is to do a draft for this CFRG on the overall concept, which is code that people can play with, and also, depending on feedback and potential acceptance by the community, probably do an IETF draft for DNS-OP, but I can't say for sure. A lot of it's going to depend on what type of feedback we get, I think.
Yeah, great. And just lastly, the algorithm negotiation, if you're interested in reviving that, so I'd be happy to talk about that.
Yeah,
Right.
and we should talk about that offline, maybe tonight. Hello.
Hello, Greg Choules, ISC. Thanks for the talk. I have a couple of comments. One is kind of in response to the comment about increased cache sizes for resolvers. In my previous job, we used to run some fairly big resolvers for a mobile operator, and the vast majority of stuff in cache was NXD. So, you know, if you can eliminate that, then I think there's plenty of space for other things. So I'm personally not worried about, you know, having to cache signatures. The other comment was about
even if they're
well,
2 orders of magnitude larger?
Yeah, I think so. The other comment was about how do you get this stuff? And, you know, one of the discussions was about maybe you carry it out of band. I think personally that's quite interesting, as if you sort of view it from the router world, where you've got a control plane and a data plane. You know, maybe we need to split DNS into sort of 2 parts and say, you know, the meat and potatoes is this stuff that the users actually want to know, but we need to know all of that stuff over there in order to make sure that what we're giving them is genuine and correct, and, you know.
Yeah, and that gets back to like on this research agenda. It's like, I put 5 mechanisms out there, suspect there are more, right? So let's get people to start proposing them, and then start studying them. What would be the impact of those? And what would actually the standards look like? And then start to say, would this really work or not based on the real world data that we're seeing? I mean, that's what this whole talk's about.
Thank you.
You're welcome.
Hi, Puneet, Sood from Google Public DNS. Hi, Andrew. So first of all, I'm not a cryptographer, so my questions are not at all about Merkle trees or any of the algorithms.
I'm not either, by the way, Puneet.
Right. So my question is from a systems level, right? DOT, DOQ are happening. Can we just as, meaning oversimplifying this, but can we look at, instead of trying to fit all the large packets into the UDP and then have to do additional complex things in the protocol, look at moving more aggressively on the secure transports, which solves the problem in a different way? And to the other question of memory size, etc., I think I would be very interested in seeing those numbers laid out with some more data around them, and also looking at how we expect hardware scaling to work in the future, right? Both how much memory and CPU servers are going to have, because if the hardware solves it for you, why do we need to solve it at the protocol and software level?
Those are all very valid points, because right now, you know, we're looking at a snapshot in time, right? So the networks operate a certain way with certain limitations and capabilities. The hardware platforms are the same. What are they going to look like in 15 years? And that sort of thing, what you're saying. And 2, what are the protocols? Like right now, I'm a little leery of session-based protocols because of the potential impact they might have on resolver to authoritative interactions, and introducing, let me finish, introducing latencies or perhaps over it. But it should be studied. And by the way, and then you're trying to project in the future. So that's why I'm saying before we pick any one path, let's study it and do a great analysis on it so that we really know. And I think quick, by the way, to me, my own personal guess is, it's probably already there, is that browser to resolver, that's going to be your protocol. But I can't say for sure. That's just my own belief. But what's it going to look like, resolver to authoritative? What's it going to look like from IoT if their stubs are interacting with the resolvers and their unlimited resource platforms, right? So that's why it needs a whole ecosystem-wide analysis, I think.
Yeah, I think I agree on the analysis, but I think we should talk offline about what experience we have between resolver and auth.
Yeah.
Thanks.
Yeah. Hello.
Ralf here from Akamai. This is more a comment to Puneet than to you. DNSSEC solves a different problem than the communication between two parties. It's data authentication. So that's why, just using encrypted transport will not help us. Encrypted transport will give us the ability actually to have larger stuff, because with DOQ, there's no problem having 5, 10K keys, because the protocol itself will split it up and will reassemble it on the event. So I don't think these are kind of either or. I think these are together working great for the future.
Well, like I said, for me, without the research, but I can envision a future where anything out of band, you're going to go over to a secure session-based protocol. And QUIC's right now the leading protocol for that, right? I think so. And then, but can we really just ditch UDP, or can we raise the MTUs on it? And what would be the impact of doing that? That needs to be thoroughly studied. Next question.
Yeah, Andrew. With Markov tree, we send the condensed signature, and I scanned the reference file. Do you think the number of requests for the reference value is a big problem?
Let me talk a little bit about that. So, when Bert introduced this concept, my boss, Bert Kaliski, probably like 3 years ago now. And my first reaction to it was, no way, Bert, you're going to be changing the Merkle tree root every time you sign. That's a no-go. It's not going to work in DNS. So we set out to model it. And we came up with some concept, which is the Merkle tree ladder mode. And I could talk offline about it. It's an interesting thing. If you're expanding your zone and you're doing it in what we call the binary build mode, publishing just the roots as you're building, so you get one big Merkle tree, then you get a little one, a little one, a little one, and you're publishing all those roots, then you're just doing merge operations. One thing is that what's nice about a Merkle tree is any reference value that you published previously, if you're doing that model, is still a valid reference value if you're just doing tree merges. So these ladders are much longer lived than you'd expect, and they have a characteristic called backwards compatibility, where if I have an authentication path that can be resolved on a ladder, I previously got a ladder that has a reference value that's part of a larger tree, and it's got all the same key tag and the same randomizer and all that. I know it's part of the same overall Merkle tree, then I know that old authentication path is still valid. So we take advantage of, I could get into a lot of detail and explain this to you, but you get surprisingly good endurance, and Bert discusses that very well in his paper, and we've actually studied some real world examples recently, and it's much better than you expect on first glance. In fact, where we're talking, for a big resolver, we're talking into the tens of thousands, even hundreds of thousands, possibly, before you need to get a new ladder.
Thank you.
Yeah, thanks. And there is one more question from the chat, and then we'll close the session. Depending on time frame, Brian Peter Dixon writes, depending on time frame, it may be better to figure out the transport limits, at least resolver auth, and getting larger than 1,500 to work to ensure DNS standards like avoid fragmentation don't prevent using larger IP packets on paths that support them.
Yeah, there's that again. Can we upgrade the networking infrastructure just to make the problem go away? That'd be great. It needs to be studied. I don't know if that's possible. All right, thanks.
Welcome back, everyone, to OARC 40. I'm Suzanne Woolf, still member of the PC, and I'll be moderator and Q&A monitor for this session. Go through the reminders real quick. We'll be taking questions from the workshops channel in the OARC Mattermost and in the room here. If you're putting a question in Mattermost, please start with # questions. Makes it easier for me to pick it out of the discussion. A poll will appear in Mattermost around the beginning of each talk and will be active until the end. This poll will be the only opportunity to rate the talks. And having that information, having your responses really helps the PC and the speakers, so please don't forget to do that. Petter will be the timekeeper for this session. Thanks for keeping us on track. And we want to also offer special thanks to VeriSign, once again, for being the 2023 OARC Workshops patron. So final point, please note that OARC membership manager, Steve Sullivan, is giving on-the-spot portal training in the foyer outside the meeting room. He is giving away free drink tickets to the first 10 people who take the short crash course. It's only a few minutes, it's good stuff you need to know, and you can get a free drink out of it. So make sure you see him to learn more. I think we're ready to get started now with the next presentation. Shumon Huque will be talking about operational experience with DNSSEC signed zones. So don't forget to watch for the poll. And
great. Thank you, Suzanne, and good morning, folks. Okay, so some quick background. A number of years ago, Pallavi and I did a talk, also at OARC, on our rationale and planning for deploying DNSSEC. And in that talk, we also described the somewhat complicated, complex nature of our DNS infrastructure. So I'll start by explaining the scope of our deployment first, and that is mainly the Salesforce core CRM application and its closely related services. Although we have other subsidiary units in the company that have also independently deployed DNSSEC that we occasionally consult with. So most notably, those are Heroku and Slack. But there are many other services that are out of scope. So anything, for example, run by our corporate IT department, like the corporate website or email, there's no business imperative specifically to deploy DNSSEC there. They're run by other teams that we don't really have close contact with, so it's kind of challenging to do that anyway. So one of the first challenges we had was due to the sheer size of our zones. So in many of our customer-facing zones, they're populated by customer and tenant-specific records. And in many cases, we have tens of millions of them. And you'll see with providers, at least that do pre-computed signatures, these are, by the way, CNAME dominant zones. And if you do some quick math, you'll find out that the record count in such zones multiplies by 4x. And if you look at the sheer byte size, it's many times larger than that still. So this kind of limits the candidate list of DNS providers that can actually handle our scale. And even the ones that could, we had to go through several rounds of performance testing and rounds of infrastructure improvements before we were comfortable enough to put our zones in production on their infrastructure. So one of the other things we need to do with zones this large is you need to do everything incrementally, not at the unit of the zone, right? So you have to do incremental signing, incremental re-signing, and incremental propagation. Otherwise, you're going to run into problems. But even then, you end up with a large amount of resources being spent simply on maintenance of zone signatures. This is quite apart from any data record updates into the zone itself. And one of the things we had to do to lessen the load further was to significantly increase the signature validity window, which isn't ideal because that also increases the window of vulnerability we have for adversaries to replay old or change records to us, but that's what we needed to do. And then to avoid large spikes of activity, we also want to make sure that the signatures expirations are kind of spread out over time, they're jittered. And we needed some improvements from bind in order to do that properly for us, which they delivered. Let's see. So this is a graph I'm showing you if you don't jitter the signatures in your zone. So you'll see there's a large spike where all the signatures are clustered together, and that's no good because what's going to happen is over time as this spike moves to the left and it reaches the re-signing threshold, which I think is T minus 10 days here, what'll happen is you will unleash a giant number of changes into your zone and corresponding zone transfers. This concentration of activity, by the way, is not just a theoretical worry. We actually caused a brief outage of a major commercial DNS provider during performance testing, right? So, and they weren't that pleased with us, to put it mildly. So what we want is, what's going on here? All right, so we want something like this, where the signature expirations are much more uniformly spread across the validity interval, and that's kind of what we strive for in steady state at least. Okay, so another issue we had was a lot of these zones have a pretty high rate of updates, at least at certain points in time. And that has caused also some aggravation with some of the DNS providers who have struggled to keep up with that rate and propagate those changes to the edges of their network within our expected time budget. So that again necessitated several rounds of performance improvements on the part of these providers. But at some point what we decided was that we really needed more precise visibility into the propagation state of the DNS vendor network. So what we did is we worked with some of the vendors to develop looking glass services, and what these allow us to do is to interrogate the list of only the active nodes on their Anycast footprint that are currently serving our zone, and then to individually direct DNS queries to each of them. So that's a pretty important diagnostic tool for us. And however, our long-term goal actually is to not have any of these gigantic zones, right? So what we want to do is we want to collapse all the tenant-specific records with a wildcard or a small set of wildcards that sends everything to a content delivery network, and then the CDN database is responsible for maintaining the mappings of tenant endpoints to backend origin services, and that, it turns out, has much better scaling characteristics. So this project is actually already in flight, and we're partly in progress using an in-house CDN that we operate, which we may in the future augment with other third-party CDNs. Okay, so what did we do about response size increases? Well, to avoid potential issues wherever we could, we tried to use elliptic curve signature algorithms, which offer a much more compact signature. On some load balancer appliances, though, they only supported RSA, and we had to drop down the ZSK to 1024 bits because, strangely enough, they didn't support anything between 2048 and 1024. And we did that mainly to make sure that all responses, particularly negative responses also, do not exceed the common internet path MTU. And we capped UDP message size to 14, I think it's 1420 or 1440 octets, something like that. And beyond that, we truncate and force retry over TCP. So the question is, did it cause us any problems after rollout? Hardly any in to my knowledge. So there was one customer case I recall where they were unable to resolve our domains after we signed them, and some quick debugging. I think within a day after this incident, we discovered the cause, and that their DNS resolvers were asking for signatures. That is, they were setting the do bit to 1. However, they had a perimeter firewall positioned between that system and the outside world that was only allowing DNS messages of 512 octets. I see a few people shaking their heads. So obviously, we know the solution, right? Fix your silly firewall, please, right? Okay, next I want to turn the topic to DNSSEC implementation bugs that we encountered. Most of these, strangely enough, fell into the same category. They all had to do with authenticated denial of existence, and we saw problems on both the authoritative server side and the recursive server side. I am going to walk you through a few prominent cases, although there are more. There's more that I won't talk about in the interest of time. So the first one is we run a set of commercial load balancer appliances from F5, and they had a bug where they used an incorrect type bitmap for their no data responses. And I think specifically they statically configured it to text or something. And my understanding from talking to their engineers is the reason for this is they do on-the-fly signing for these dynamic responses, and that layer of code doesn't have an efficient way to poke into the backend database to figure out what's actually there. So this is the reason. And this kind of work, these kind of made-up type bitmaps work fine until what happened? Until the emergence of resolvers that implemented aggressive negative caching, specifically with type inference, right? That's when things started tripping up. So what the vendor did was to introduce configurable options where operators could specify what are the known types of records at those names. And that kind of fixed the problem. Although that wasn't the end of the story, there was episode 2 of this problem, which was a little bit of a variant. And this had not to do with no data responses, but NX domain responses. And this was brought to my attention, incidentally, by Peter van Dijk, who I think is in the audience somewhere probably. And this is best illustrated, I think, with an example query and response. Okay, so don't get alarmed. You did not walk into a DNSSEC protocol tutorial. I'm just showing this slide for reference because I just want to point out a few high-level things. So we have the first line, we have a domain name that has an address record, the load balancer addresses. And the second record is something underneath it, foo.something, which doesn't exist. But what happened is if you queried the second thing, you would get an NX domain response, but in that response would be included, and this is required by the protocol, an NSEC3 proof for the closest encoder, which had an empty type bitmap. So aggressive negative caches, what they could do with this information is infer that the first record doesn't actually exist and send back NX domain, right? So obviously, no data. So this is obviously no good. This is broken. So we worked with F5 to get this fixed. This one, it turned out, can I go back? It took us a little bit of a time to fix it because we had to wait a few months for the vendor to implement the fix, and then several months after that for our network operations people who actually run the F5 appliances to put the thing into practice. And in the meantime, what had to happen was the ISPs of the customers that were experiencing this problem, they had to install negative trust anchors for us, which isn't ideal, but that's what we had to do. All right, so now I want to talk about a problem in an open source implementation. And the situation was that PCH, one of our managed DNS providers, they introduced not DNS as a second implementation into their footprint in addition to what they already had, NSD, ostensibly to solve some performance problems they were experiencing. But within a few days, we got critical complaints from customers that they couldn't resolve our names. So the names had a particular form. It was a little bit complicated. These involved a wildcard CNAME that pointed to another CNAME that pointed to a name in a delegated zone that was unsigned, right? So, you know, at that time, right? It's signed now. But the NSEC proof for this is a little bit complicated because it requires two different types of NSEC3 records. One, to prove that there was no closer match than the wildcard, and the other to prove insecure delegation. And what was happening was failing to include the first response, so it wasn't authenticatable. So the question is, what was the impact on DNS resolvers? And you might be asking yourselves, as I certainly did at the time, that, well, so what? I mean, the provider had another implementation, NSD, that was giving correct responses. And on top of that, we had a second provider that was Neustar's XTLD platform that was running a third implementation that was also giving the right response. So wouldn't we expect resolvers to be robust against the situation? If they encounter an unvalidatable answer, they should requery other authoritative servers for the zone until they get a proper answer, right? And in fact, during this incident, every resolver that we tested had this robust behavior. And yet, we know that we had customers that were running some species of resolver that was not robust in this condition and failing catastrophically, right? So at that time, this was kind of a This is a very important customer. This was kind of a pants-on-fire emergency, so we had to fix the problem right away and didn't really have time to investigate what resolver they were using, right? So the fix, as it turns out, was a little bit more involved than I had anticipated. So our first move was to remove the problematic provider from the NS set, and which worked modulo TTLs, but as luck would have it, a few days after that, the sole remaining provider came under a sustained DDoS attack, and we had to do emergency fix number 2, which is, I recall, getting Bill Woodcock on the phone and explaining to him, okay, we have another emergency, we need to put you back in service, but you need to excise the second implementation entirely from your footprint. And it turns out they had automation that could quickly withdraw the Anycast route advertisements for only those nodes, and we were back in business. All right, so I don't mean to pick on any particular vendor because, as I explained, these are widespread across many implementations. We learned from PCH after this incident that they had almost the same problem with NSD the prior year, and NSD had to fix that same problem. And I'll mention one incident on the resolver side, and this had to do with Google Public DNS. And this was, again, with a rather complex configuration involving CNAME chains, wildcards, and delegated zones. And this one was compounded by the fact that we had a parent and child zone co-located on the same authoritative server, and they were giving combined responses, and Google Public DNS didn't know how to deal with this situation, right? So in this case, we actually found some workarounds for the affected customers until Google was able to implement a fix, which was in a few months. So let's move on. And I think everyone remembers the Slack DNSSEC outage, which got a lot of press coverage. I think it was talked at OARC too. So I'm not going to rehash that here in the interest of time, other than to point out that this was yet again a problem with authenticated denial of existence, right? And let me skip over this protocol minutia and move on to the following question, which is, why have we had so many bugs in authenticated denial of existence? And these have plagued, as I mentioned, many different implementations almost across the board. It seems to me, if I think intuitively, that we could design, implementers could design a comprehensive DNSSEC test suite that should be able to catch every single bug that I mentioned here, right? So are we not doing a good enough job in this area? That's one question I have for you guys. And the other thing is the subset of these problems that involve incorrect type bitmaps is also very interesting because you know, it used to be that implementers could play very loosey-goosey with the type bitmap and get away with it with no impact. And it wasn't until the emergence of the aggressive negative cachers that this really became a problem. And you can take the position that they should not have been doing these things, right? And it's their fault, but I don't really think that's a helpful stance. And I'm wondering if we should have done something better and more deliberate and more careful, such as maybe a flag day preceded by a comprehensive study of ecosystem-wide impacts before rolling out features like this. All right, so what could help? So obviously the first thing is we need better test suites, right? But we can also enhance name server troubleshooting and diagnostic tools to do a better job with DNSSEC. I think there was a presentation recently by a bunch of academic researchers, which is a good tool that detected protocol compliance bugs and implementations. It did not handle DNSSEC though, so that could be an area where more work could be done. The other thing I'll mention is DNSViz, incidentally, can catch many of these kind of errors, right? If you turn on denial of existence checking, which by the way isn't the default and really should be. So I've had some discussions with KCDCO in the past, and I reminded of him last week when I was working on this slide, and he agrees, and he's working on fixing that default. So I hopefully that will provide people with a better diagnostic tool to catch these kind of errors early. And then I mentioned, I wanted to quickly touch on name server provider change agility. So many of the issues that I talked about, we worked around by swapping in and out DNS operators. And so longer term, I think TLDs really need to provide mechanisms to allow registrants to set custom delegation TTLs when they need to. There is some work in this area going on with involving an EPP-TTL extension that may facilitate this. Similarly, we need agility with DS records as well to address some of these problems. You can also imagine that resolvers may at some point take matters into their own hands and say, okay, we're not going to honor any TTL larger than this small value to work around these problems. So really we need to cooperate and make sure that the outcome that we want is actually what happens. And I'll end with some parting thoughts and advice. So in our experience, if you want to deploy DNSSEC in a complex enterprise network, at least at its current state of maturity, you really need substantial expertise on your staff today, right? Even if you outsource the operations to third parties, because trust me, you will be spending a lot of time debugging and troubleshooting various implementations out there. Knowing key DNS folks at other companies and open source projects, that has helped us a lot, and it will help you too. You need to pay a lot of attention to the testing of authenticated denial of existence, which is a recurring problem area. My advice is do not use DNS zones as gigantic application configuration databases. They're not really designed to do those things, and at some point sooner or later you'll run into scale issues. And if you use multiple DNS providers if you can. It's helped us many times. And if you have online signers, ask them to implement multi-signer DNSSEC. And with that, I will stop and see if there are any questions and comments.
Hi, Shumon. Lars Lehmann from NetNode. Thank you for this very interesting presentation. Is there any chance we can, NTCU to tickle you into compiling a more comprehensive list of the problems you ran into so that other people can benefit from that when they test DNSSEC and specifically authenticated denial of existence?
Yeah, I think I would be open to providing that information. I have to be a little careful because we need to redact any customer names and stuff in zones. But I want to remind you, Lehman, there is a project like this, which is, I think it's the DNS violations project, right? Where people have been compiling a list of breakages. So, I think my preference would be just to reuse that. If I can contribute other breakage cases that I'm aware of that are not in that list, I could add to that list.
Perfect, thank you.
We're trying to alternate between questions in the chat and questions in the room. Question in the chat from Victor Duchovny. Were the load balancers that don't support, say, RSA 1280 signers or validators?
Sorry, I didn't catch the last part of Victor's statement.
Were the load balancers that don't support, say, RSA 1280 signers or validators?
So in our case, they were signers. So these are F5 GTM devices that are basically authoritative servers.
Hey, Shumon, Puneet, Sood from Google Public DNS. So thanks for this. I think this is very illustrative of the kind of issues which happen with DNSSEC in the real world. As I tell new people on our DNS team, DNSSEC is a collection of edge cases, unfortunately. So I think the key point, even for myself, is that the rules on what to do is spread along a bunch of RFCs. And as I like to state, English is not an algorithm language.
Yep.
What we really need is a central place where some of these things are written in a way that mere DNS implementers, not DNSSEC experts, can take those specifications and verify that their implementations are doing the right thing. This is where I would point out, I think Paul Hoffman mentioned he's driving an effort to annotate RFCs with expert opinions. I'm not sure if Paul is here, but I think maybe that or an idea of something like a DNS wiki or somewhere where experts write things down in a easier to follow way, which doesn't have the same bar as getting your update through the DNS-OARC or working group basically approval process, because it's a very slow process. Right. That's one thing I think for sharing knowledge. The other, as you brought up the TTL slide, I think mic line is too short to contain the discussion there, but that's something we are also very interested in looking at. Lower TTLs, serve stale, and other mechanisms to just make bad records disappear faster from the caches.
Yeah.
Something we can talk more about.
Sure, yeah, certainly, let's talk. And I agree with you, your first point about making things more intelligible to implementers and things of that nature.
So next question from remote. Did you use a big jitter time to get the graph from slide 8?
Did I use a big jitter time?
Yeah.
Yes, I used a big jitter window, right? Because I think in that graph, if I remember, it's something like 40, 50 days, right? As I mentioned in my prefatory remarks to that slide, that's not ideal. Ideally, you want the signature validity window to be as low as you can handle, but it's not possible with pre-computed signatures and enormous zones, right? Because the amount of churn you're going to generate in the zone is going to be insanely high.
So Ed Lewis, I can. One of the things I've been curious about for the past couple of decades is why do protocols that are so well designed not operate well? I don't want to make jokes about that, but we know what's going on. But looking at this, I'm wondering about, there's one thing I want to point out, two things that came to mind, but one thing I wanted to point out was, it's curious that a lot of the issues with these bitmaps seem to be a result of people doing assigning on the fly responses to do things,
yes.
Right? Which is actually a brilliant idea. And I think it's great if you can sign on the fly. But NSEC and NSEC3 were both designed assuming that would never happen. And so I see right there a collision between how we operated something that was designed to be done a certain way. And I wonder if that's a root cause eventually of these faults out there. So I'm just putting this out there as I want a thing to look at, because I hear a lot of other reasons for things not deploying, but this, I haven't seen such a deep dive into actual technical issues like this. It's good to see the laundry list of this thing, of these issues, as opposed to things just don't deploy because I don't have permission or whatever. The other question I have is, I also have come to realize that in protocol design, we like to design these protocols that can do anything. We just change configuration flags. It's very amenable to every situation out there. But in operations, you want to keep things simple.
Yep.
So another point here with the NSEC, NSEC3 is that we have two choices for negative answers. And I always wonder if that makes it complicates the implementation, because now the implementer has to know whether this is going to be a zone sign this way or that way. That's another point where I wonder.
Yeah, I agree. So I don't know if I have a conclusive answer, but I think your first hypothesis is probably true, that it has to do with the online signers and using shortcuts and things that are easier for them to do, right? So yeah, I mean, I think that needs more investigation, certainly, right? So the type bitmaps, as we know, they can no longer play loosey-goosey with because of resolver implementations out in the field today. But other things, they use other tricks. So in the Slack slide that I showed, there's a protocol minutia slide where I showed Slack's problem was with a wildcard no data response. But any DNS protocol expert looking at the response that I showed you will say that's not a wildcard response, because it has no wildcard proof in there, right? No closer match than the wildcard, right? Because the online signers, they don't have to pre-compute anything. They can pretend that all records that existed that match the wildcard actually existed in the zone and produce a signature on the fly for them, right? So these things are all possible with online signers today. And I agree, I think these were not envisioned when DNSSEC was first designed.
Yeah, and the other, I guess you were talking about the response side. I think you covered response side. Maybe it was a presentation. But NSEC, NSEC3, the NSEC3 needs an extra response. I don't know if that's, there's also things to pick on here. But I think we have to go back sometimes and see what was okay, I get the better. We did look back sometimes at what was designed and how it's being used and fix that too. So.
Yep. Okay, great. Thank you very much, folks.
Thank you. And next up, we have Brian Summers to talk about DNSCrypt protocol, current state and planned extensions.
Okay, my name is Brian Summers. I work at OpenDNS or Umbrella or Cisco, take your pick. And myself and Dahan Donan have been doing some work with a bunch of other people in Cisco on DNSCrypt. So I'll talk a little bit about what DNSCrypt is at the moment, about the things that I've discovered in our kind of journey towards writing an RFC for DNSCrypt, and then finally why we're writing the RFC, what we want to do in terms of extensions. So I'll talk a little bit about the RFC, not in a great deal of detail. We haven't publicized this to anybody yet. This is the first time we've communicated this to the outside world. And I'll kind of talk a little bit about our DNSCrypt performance at OpenDNS, which is a little bit embarrassing. So DNSCrypt background. So it's been around for a long time. It's been around for 10 years or thereabouts. And it's got quite a few supporters in the community, Quad9, Umbrella. A number of free vendors will talk DNSCrypt to clients. There's a ton of client implementations. There's a website called DNSCrypt.info that I'd invite everybody to have a look at that does a great deal of kind of good job of detailing all of the available implementations, whether it's public domain source code for the client or server side, or whether it's public services that are available. So DNSCrypt is all about the last mile. So by the last mile, I mean this piece on the left. So the conversation between the client and the resolver. DNSCrypt doesn't cover anything between the resolver and the authority. That's DNSSEC's problem. So DNSCrypt really was kind of first invented to complement DNSSEC. I'll just go back to the previous slide. So what DNSSEC does, what DNSCrypt does, it would help if I actually talked about the correct protocol. What DNSCrypt does is it authenticates and encrypts. So it makes sure that if you're a client, you're talking to the server that you think you're talking to, otherwise they can't respond to you, and it encrypts so that if there's anybody looking at your traffic, they can't see what you're asking. And the idea behind DNSCrypt is that it's encryption of the payload. So it retains all of the expected characteristics of DNS. So we query over UDP. If the response is too big to fit in your UDP buffers, then you get the TC back, and then you query over TCP. That continues to behave in exactly the same way with DNSCrypt. And there is one kind of consideration. Once you encrypt packets, you tend to use padding, block padding usually. DNSCrypt is no exception, so queries will be block padded to hide the size of the queries that are being sent. So there is a bit of overhead there. So of course, in the last few years, we've had a ton of other efforts at encryption. Raising, well, I guess DNSSEC is somewhat older than the last few years, and that's a different part of the end-to-end security problem. But really on the front end, for the last mile, we've got DNS over TLS and DNS over HTTP. And of course, we've got DNS over QUIC and DNS over HTTP3. So I'll talk a little bit about them and what they're good at and what they're not very good at. So DNS over TLS is kind of my favorite of the transport layer responses to security. I like it because it's just got the transport layer security added on. It doesn't have anything else in between. It does attract an overhead of establishing that TCP connection and doing the TLS handshake, but it actually claws all of that performance degradation back by stuffing multiple queries and multiple responses into individual packets. So the net result is, I think lots of other people have talked about this, that if you send 7 or more queries over your TLS connection, then your quid's in terms of performance. One of the big problems with DOT or DNS over TLS is the head-of-line blocking issue. Once you use TCP, if you drop a packet, you've got this head-of-line blocking issue, and you've got to retransmit that packet before you can continue on, and any queries that are sitting in the stream after that have to wait. DNS over HTTPS has all of the same characteristics as DOE, except it's got this protocol layer in between, and the protocol layer is an HTTP2 protocol layer. So that's kind of like HTTP, but in binary. HTTP2 does a little bit extra, though. It also does this session management, and this session management is really handy for clients because it's actually quite tricky when you're talking over TCP and getting responses in different orders to the queries, so out-of-order responses. It's sometimes difficult from the client side to write code to marry up those queries and responses. HTTP2 solves those problems for you. It makes that part of the protocol. And DOC and DNS over HTTP3, I haven't had much experience. These are two protocols that are analogous to DOT and DOE, except their versions over QUIC. And of course, the DOE3 is DNS over HTTP3, which is implemented over QUIC as well. And QUIC is this newfangled, which is getting quite old at this stage, mechanism whereby we're doing the TLS layer, we're doing the identity management or encryption reestablishment, and we're also doing the session management all in one QUIC layer. So it solves a lot of the problems. Specifically, it solves the head-of-line blocking problem. And as was already mentioned in a previous talk here, I really have the opinion that DOC is going to be the way of the future for clients. Anyway, going back to DNSCrypt, I'll just kind of fly through this slide. So this is really what happens with DNSCrypt. So the idea behind DNSCrypt is that you have some well-known providers out there. And they're well-known in that they have a well-known public key that your client has to be aware of. And the way the protocol goes is the provider will create this short-term key pair. By short-term, we use that term loosely for the server side. Short-term is a year in our case. I know that Quad9 use a year as well. Lots of the other vendors use something that I wouldn't really consider short-term. But anyway, it's medium-term, maybe a key pair. So the idea is that the server will generate this key pair and will publish the public key as a certificate or in a certificate and make that certificate available in a well-known location over DNS. So you query this certificate using a text query, and you get your certificate back, which contains the public key that you should encrypt traffic using. The client for DNSCrypt also has a key pair. So they have a real short-term key pair. It might be a few minutes, kept for a few minutes. It might be kept for an hour, but it's measured in minutes or hours rather than in months or years. So that key pair is generated by the client, and the way DNSCrypt essentially works is that both the client and the server will generate a derived key, and that derived key for the client is the client's private key and the server's public key, and for the server it's the client's public key and the server's private key. So you get this key pair that can be used to encrypt and decrypt traffic between the two. And essentially the client will obtain the certificate, keep the certificate for an extended period of time, usually half an hour or so, and will use that derived key to encrypt traffic to the server, making it nice and quick. DNSCrypt is on version 2, so that's a protocol version 2. This isn't the updated version of the slide. So protocol version 2 contains two possible encryption system versions. So that protocol version in the top left of this slide should say encryption system version or ES version. So there's two encryption versions which are shown in this slide. And really they're just big long names that define the crypto functions that are used for key exchange, for signature validation, for secure hash, and for the encryption itself. And the only reason there are two encryption system protocols, or versions I should say, is because SALSA was originally used as the secure hash mechanism, and that was changed to ChaCha at some stage. So the interesting thing about these is that they have public key lengths of 32 bytes. They have signatures of 64 bytes, and that's because we use EC25519. And they have a kind of fixed size nonce MAC or IV. So anyway, with all of this in mind, we started kind of writing this RFC or proposed RFC, and started looking into the way our code works. And this is the piece that I find really interesting. So I did some performance measurements on our code, and we have two graphs here. And the summary of the graph on the left is that this is a snapshot of DNS traffic on one of our machines. And the light blue is plain text DNS traffic. So it's about 2/3 of the traffic. The dark blue is DNSCrypt traffic, which is about 1/3 of the traffic, and the yellow is authoritative queries. And the same slice on the right represents the cache behavior during that time. So the light blue, that big chunk in the middle, is the cache behavior where we have one client response and 0 upstream DNS or authoritative queries. The green stripe kind of near the top is where we have one client response but one upstream authoritative query. And the red at the bottom is because somebody was attacking us at the time, so they were actually sending us queries, but we were sending 0 responses to them. We were dropping their traffic on the floor. And there's a band of color at the top where there's more than one authoritative query. So in this scenario, really, we have a resolver that's sending and receiving queries, and really about 2/3 of the traffic is plain text, and about 1/3 of the traffic is DNSCrypt. So there's a tool called perf that you can run under Linux, and one of the functions of this perf tool is you can generate these flame graphs. So I generated a flame graph for this period, and I was kind of curious as to what we're actually spending our time doing. So I know this slide isn't very easy to see, but we can look at the shapes more than anything. So this is really kind of trimming things down to our server process, which is called OpenDNS cache. And really what the server process does is it spends most of its time starting a worker thread, loading configuration, which is that kind of series of spikes over on the left. And then really the FD event dispatch, which is that yellow stripe that goes across the middle, kind of about 4 lines up, is the main kind of bulk of the work. And the piece on the right is FD event wait, so that's where we're doing nothing. We just put our finger up our nose waiting for queries. So we're not slammed, we're not inundated with too much traffic. So that FD event dispatch, so most of the time we spend doing unew. And unew is the function where we get a new UDP query. And that new UDP query will try to do something with that incoming query. So it'll either obtain a response from the cache, or it will decide to send something upstream. And of course, if it sends something upstream, that becomes an FD event, and at some stage later, it will come back with another FD event, which is the response to that upstream query, and it will go off and handle that. So you can see that yellow stripe kind of is primarily unew, and as part of that unew, on the left-hand side, you can see I've kind of highlighted the DNSCrypt uncurve piece, which is the piece that decrypts the incoming queries. And you can see, like, on that unew kind of slice of CPU or performance, that DNSCrypt is, quite a chunk of that. And the rest of it is query start. Query start is the thing that goes and looks at the cache and serves the response from the cache, or actually query starter looks up the cache and may come back with a response, and UNU may send that response to the client. So we can see over on the right-hand side, the two things that I've highlighted are the places where we encrypt the response. So one of them is in UNU, where we're encrypting a response that comes from the cache. And the other one we don't care too much about for these purposes is where we encrypt the response that comes from an authoritative response. So zooming in on those encrypt and decrypt functions. So this is the really interesting thing that kind of appalled me. Didn't shock me, but it appalled me, is that most of the time that we spend encrypting and decrypting these queries is in this before NM function. And before NM, if anybody has ever been in libnacl or libsodium, which does all of these, or implements all of these encryption algorithms, before NM is the bit that actually figures out the derived key. So it's the thing that basically slams together our private key and the remote's public key into one derived key. So this kind of highlights that for all of these years, like since 2013 or thereabouts, we've basically been failing to cache the derived key. And this matters hugely because like 90% or 95% of our time is actually spent deriving this key and not actually doing or performing the encryption or decryption. So anyway, moving along, the whole purpose of this work. So this work is all about FIPS encryption. So FIPS is this thing invented by NIST in the US. It's all about being able to talk using supported algorithms for the purpose of talking to government sites and conforming to what they consider secure encryption. I won't go into my opinions of FIPS, but one of our requirement was to be able to support FIPS algorithms. And of course, the algorithms and secure hash ciphers that are used in DNSCrypt aren't FIPS compliant. FIPS doesn't include EC25519 yet as a compliant algorithm, and certainly doesn't allow things like poly1305 and SALSA. So anyway, the whole purpose of this DNSCrypt, or this work, is to create a DNSCrypt version 3, and this would just essentially define a new protocol. The most interesting thing about the new protocol, of course, is that involves a bigger public key. Even the compacted public key for P256 is 33 bytes, which is a different size, which will upset everybody that currently does DNSCrypt. So we've revised bumped the protocol version to version 3, or intend to. So the other two interesting things that I found about the algorithm or the DNSCrypt version, which I'll quickly cover, is padding. So DNSCrypt claims to be capable of blocking amplification attacks. We looked into this. We've never supported this in Umbrella. We're called out on DNSCrypt.info as not supporting it and being non-compliant. But the way you're supposed to support this is by implementing a server that says if the response is bigger than the question, then you send a TC. And implementing a client that says if you get a TC, then you maintain a minimum query padding size, and you bump that minimum size so that it's equal to the response that you get back when you query over TCP. And in my view, this is ridiculous, because it just basically means that your DNSCrypt client sends all of its queries padded to 1,300 bytes, give or take, for IPv4, IPv6. That's not a good way of dealing with amplification attacks in my book. This needs discussion with the community. Maybe I'm missing something. And then certificate renewal, it's very badly described. It describes it as you should renew your certificate every now and again, every half hour. And our kind of take on that is that we should tie it to the TTL of the certificates that we're actually doing. So that's all I've got. There's some references there if people want to click on links. And I'll take questions.
I'm not seeing questions in the chat, and there doesn't seem to be anyone waiting in the room. Ah, okay. We do have a question in the chat. Paul Hoffman asks, where is this being standardized?
Nowhere yet. At the moment, we have an RFC proposal, but it's been kept within Cisco. So we're still going through grammar checks and trying to make it a little bit clearer before we bring it out into the community. I think before we kind of try to make it into a draft RFC, we'll probably touch bases with people like Frank Dennis on the DNSCrypt.info site to kind of resolve some of the kind of questions we have around the Protocol 2 implementation.
Thank you.
Thanks very much.
Anyone else? Guess not.
All right, everybody. Welcome to session 3 and 4 of OARC 40. I'm Manu, and I will be sharing these afternoon sessions. We have William with us that is going to be doing timekeeping. A few announcements before we get started. Q&A. If you are in the room, please go to the mic when you ask your questions. If you are online remote, please ask your question in Mattermost and prepare your question with #questions. And I will be asking them for you. We are accepting lightning talks for tomorrow, and the CFP is open until 11 a.m. tomorrow. We're only taking local speakers for the lightning talks. We would like to thank VeriSign for the sponsorship of the workshop. And we have Steve Sullivan here that can do demo of the portal, and you will get free drinks if you are one of the 10 first one to get there. So please go and check him out outside. I guess I'm done with pretty much everything I had to say. Oh yeah, no, sorry. Paul, during the talks, there will be a poll coming up on Mattermost. Please, give a thumb up, down, so we get a good idea of whether or not you like a given talk. And I guess with that being said, I think we're pretty good to go for the first speaker. So Chang Li. So Chang Li from Tsinghua University is going to talk about DareShark, detecting and measuring security risk of hosting-based dangling domains.
Hello everyone, I'm Xiang Li, a PhD student from Tsinghua University. And today I will share a guide with our latest research on the domain takeover topic, where we design a new detection framework called DareShark to detect and measure the security risks of the hosting-based domain takeover. And to start with, we all know that domain plays an important role in today's internet and provide a solid basis for multiple applications and services. And according to VeriSign's stats, sorry for the delay. There are about 350 domain names that have been registered. And however, domain parts cut both ways. They are often abused to do some criminal activities, such as botnet communication, phishing, and etc. Especially, attackers could use some domain outside their authority to do some maybe malicious activities. And one of the powerful ways is domain takeover. So what's domain takeover? Domain takeover works like the user-free bug. So when a user tries to add his domain to a service platform, for example, he needs to add a CNAME record to the name server. And after he connects the domain to the service, and everything is good, and the service works well. Afterwards, if the user no longer wants to use the service, and he just canceled the service, and but forget to remove the CNAME records. So such a record becomes a dangling record. And after that, the attacker can just apply the same CNAME alias and connect the victim domain to the hosting service. Then, because of the existing CNAME, such a domain is controlled by the attacker. And referring to the paper from CCI 16, we also call these security sensitive dangling records DARES, such as the type A, CNAME, and NS. And over these years, many domain takeover incidents happened, and even for large companies like Microsoft. And we are wondering why domain takeover are still prevalent. And among these websites, we find the hosting-based hosting services takes a majority and continues to growing that becomes the potential domain takeover targets. So in our research, we try to narrow down the vision to the hosting-based domain takeover threat. So first, I want to explain what the hosting-based domain takeover is. So for a hosting platform, to use such a service, the user, let's say Alice, she wants to add his or her domain to the platform. And the platform just assigns a token, like a TXT value, for Alice to configure and to validate the domain ownership. And after Alice add the TXT value to the name server, and the platform passes the validation, the platform could assign endpoints for Alice to connect her domain to the platform. Then Alice just adds another connecting domain, like a CNAME record to the name server, and connect her domain to the platform. And in doing so, the service runs. In the end, the service is hosted. However, a hosting-based service might be vulnerable if the platform has no or valid offload domain ownership validation, or the attacker could reuse the same endpoints from the victim user. So in these cases, hosting-based domain takeover could happen if the victim user forgets to remove these assigned records, and which becomes the dangling record. And so here is the domain takeover procedure. So in step 1, attacker wants to add the same victim domain to the platform. The platform just assigns the same records, including the token and the endpoints for the malware to connect. And because of these dangling records exist, such validation is passed, and the attacker malware could control the victim domain. And that's the hosting-based domain takeover. So meanwhile, we wonder why domain takeover occurs ceaselessly. And we found 2 main reasons. First, it's not easy to identify all the hosting-based domains because there are various domain hosting services and hosting strategies. And the active domain resolution has limited efficiency, so a generic method is needed. And second, an efficient detection system is absent for quickly and timely detection, since there are thousands of subdomains even for just one base domain. And any node in the DNS resolution chain could cause the domain takeover. So can we solve these challenges? I think the answer is yes, because all the domain features we need to identify third-party hosting services and to identify the vulnerable domain is logged in the passive DNS traffic. So here are our observations. First, we find that the hosting services all have the same endpoint patterns. I think we can use these common service endpoints to identify hosting services. Then, to reduce some false positive, we can use some domain characteristics such as the domain dependence number to filter out some small services and that has less pointed custom domains. So lastly, our solution for the domain takeover detection is to use the passive DNS traffic to automate our approach to discovering and identifying vulnerable domains. So by doing so, we design a novel framework called DareShark, and it can help us in 2 ways, including discovering the vulnerable hosting services and to find vulnerable domains efficiently. So here is the workflow of DareShark. And DareShark has 2 parts. Part 1 is the offline vulnerable service discovery. So in step 1, we use the passive DNS to find the potential third-party services endpoints, and then we extract these common endpoints. Third, by manual analysis, we can identify all the vulnerable services. Then we maintain a vulnerable service DB for the path to the detection. Then for part 2, we try to detect the vulnerable domains timely. And for each target domain, we use the passive DNS traffic to collect all its subdomains, and to reconstruct the DNS chain. So for each record in the DNS chain, we can apply our vulnerable service DB to identify potential third-party services and apply our fingerprints to identify the vulnerable domains that could induce domain takeover. So in the end, the detection report are output. So in detail, for part 1, we use passive DNS to find the potential third-party service and candidates, and we leverage domain resolution popularity and domain dependency for service endpoint discovery. Then for each endpoint pattern we found, we construct a domain suffix tree following the structure of domain namespace. Then for each node in the domain suffix tree, we calculate their tree attributes, including such as the number of subnodes. And for example, the node 1 at level 3 has 3 subnodes. Then we prune the domain suffix tree from bottom up to filter subdomain nodes have more than 1 subnode until only 1 leaf is left. And the left node and its domain name are considered as the longest common endpoint suffix. Then in step 2, for each service, we extract their common endpoint pattern. And each service may have more than 1 services. Then in step 3, we try to identify the services and check their vulnerabilities. And through extracting the points from the domain suffix tree, our manual analysis can be largely reduced. And we also remove some highly randomized patterns and checking their domain validation methods. And in step 4, after checking all the services, we can create and maintain a vulnerable DB to cover all the vulnerable services and their fingerprints, including the HTTP and the DNS. Then in part 2, we try to discover in all the hosting-based DAREs. And with passive DNS, we can collect as many as subdomains of the target domain and to reconstruct their DNS resolution chain. Then for each record in the DNS chain, we use the endpoint patterns to identify whether they are using the third-party services or not, and use our HTTP and DNS fingerprints to identify some potential domains by active accessing them. So in the end, we can, with double check, we can identify all the subdomains that have the takeover threats. And here are some examples from the service of Webflow, Fastly, Cloudflare, and AliCloud. So after we design the framework, we employ DareShark with a large passive DNS data set, which contains more than 600 billion queries per day and covering more than 99% of trunk top 1 million domains. And we find we have 2 main findings. And for the part 1, we find that the current practice of hosting services is in a mass, and which comprising a variety of vulnerable services that can be used to do some domain takeover. And in total, we identified 65 services vulnerable to the domain takeover threats, which comprise a variety of tabs, such as cloud storage, CDN, and website builder. Among them, we summarized 9 domain connecting methods, and some of which are exploitable, such as some connecting methods use fixed endpoints, and which is very easily to be takeovered. And we also identified the 4 types of domain ownership validation issues, and attackers can just leverage them to bypass the domain ownership validation method. And among them, especially, we find that the top 20 vendors with more than 70% market share are vulnerable. And we just list some of there. And for all the listed vendors, we have reported them to the vendors, such as Ali, Baidu, Cloudflare, Fastly. And for the part 2, we find the hosting-based domain takeover threats are still prevalent. For this part, we conduct a large measurement for the trunk top 1 million domains and subdomains under the EDU and the GOV TLD. And we collect more than 11 million subdomains. And for all the subdomains, we conduct a longitudinal measurement from December 21 to July 22. And the results show that more than 114K FQDNs have been vulnerable on these vulnerable services. And more than 10K FQDNs are actually vulnerable. And we double-check these FQDNs by active access their websites and do some DNS resolution to see whether they followed our fingerprints in the vulnerable service DB. and including some reputable universities and companies. Besides, we found that the hosting-based domain takeover are still prevalent, and they appear frequently and long-lasting. Because for these, we found we could find new vulnerable domains every week, and over 50% of these domains can be vulnerable for over 10 days. And here, at the conclusion, we designed DareShark, a novel and effective hosting-based domain detection system, and which had a high efficiency and coverage. And with DareShark, we did a comprehensive measurement to discover and identify vulnerable domains for trunk 1 million subdomains. And in the end, we detect more than 10K vulnerable domains, which is 8 times more than previous studies. And in doing so, we also did a systematic service analysis and try to find which services is vulnerable or not. And we discovered 65 vulnerable services with that has never been reported before. And we also report our findings to all affected vendors and received confirmation from 10 vendors and provide a detailed solution to these vendors. And we hope our study could help to resolve the domain takeover threats and maybe urge the community to do some short-term or long-term measures to mitigate these threats. And this is my share today. Thank you all for your attention. Thank you.
Thank you, Chan.
Okay.
So anybody in the room that want to ask a question, please go forward to the mic. In the meantime, I will start asking the questions which were posted online. First question from Victor Dubovnik. Have you considered also looking at certificate transparency logs for candidate domain names?
Basically, yes. And we try to, first we use the passive DNS. Maybe it include all the responses sent to the clients.
And the next question from Patrick Mevzak. Why not using the PSL, which is a public surface list, to extract the base domain of provider services? Of course, it is not exhaustive.
That's good question. So first, while we try to analyze the hosting services, because as mentioned before, hosting service may take a majority, maybe market share, and may have a huge impact. And basically, our idea is to find some maybe new vulnerabilities. And why we choose that is hosting-based services have many bug reports in the HackerOne platform. And we try to provide maybe automated way to find and maybe to solve this problem.
Yeah, and that's going to be, I guess, a comment from my side. I guess it could be a good seeding resource, or it could also be a good resource to confirm how your logic work in matching them.
Yeah.
There's no question on the line. I got one, actually. Typically, people ask that one. Is this open sourced, or are you planning to open source it so people can use your tool?
Yeah, it's open source. We list the link in our paper, but the paper maybe...
Okay, it wasn't there, okay.
Yeah, we will open source it maybe in a few days. Yeah.
Right. Thanks a lot.
Yeah, thank you all. Yeah.
All right. Next, let me introduce Shannon Weyrick from NS1. He's going to talk about how Orb power NS1 DNS Insight and how it could also power your own analytics.
Thank you. Okay, hello everybody. My name is Shannon Weyrick, and my talk today is about Orb, something I've spoken about a few times at OARC, and this is the latest iteration. It's about how we've taken Orb and built a product out of it. So I am going to give a quick history and give some context for those who may not have seen it before, talk about what Orb is, what DNS Insights is, and what the difference between those things are. And then I'll get into a bit of practical architecture, how Orb is built and how we used it to build out the product itself. And at the end of the slide deck, there is an appendix which has a practical application of using Orb, actually setting up some policies and debugging with it in real time. I probably won't have time to get to that in this talk, but please check out the slides. And I'll certainly be around afterwards if anybody has any questions. Okay, so a quick history. So what is Orb, who is NS1, and so forth. So let me start with NS1. So NS1, if you haven't heard of them, is a managed authoritative DNS provider. We are obviously serving any cache traffic around the world, and it's a platform that has given us the opportunity to build tools to manage, to help us operate DNS networks. So one of the things that we've been doing for the last few years is called NS1 Labs, and we've been working on some open source projects. I've spoken in particular about the PacketVisor project, which is our edge analysis tool. So it's doing the packet analysis and other things these days. You can see my talk at OARC 33 if you'd like a deep dive on that. And on top of that, we've built Orb. So that's a platform that has started to add a control plane and other things that I'll get into. And so that whole thing is Orb. It's an open source network observability platform that's come out of NS1 Labs, which we've now brought into a brand we call NetBox Labs. And so, what is DNS Insights and how do they relate? So what we've done is we've taken Orb and we've built a product around it called DNS Insights. And so for NS1 customers, we're starting to give all the value that Orb has, that our operators have been using, and be able to deliver metrics and telemetry directly to NS1 customers. So in the end, what does Orb give you? Orb gives you metrics. Orb gives you telemetry and graphs like you see here. And so that's going to be very deep on the DNS side, obviously. So not just query levels, but response codes and top N of various range of things that operators care about. And so again, I spoke about this a bit already in a previous talk, but there are other tools out there that do this. Undoubtedly, most of you have some kind of analysis on your DNS networks. But we think Orb is a little bit different. Orb, for one, pushes analysis to the edge. And so all of the analysis that's happening inside of Orb and inside of the PacketVisor tool is happening at the edge, directly at the query source. And the whole system is built to be very dynamic. And so we're able to customize in real time policies, or what I'll call edge queries later in the talk, and reconfigure a fleet of agents that are observing the traffic along the Unicast network in real time. And then on the other side of that, we have a very flexible and dynamic way to take the telemetry and the metrics that it's coming out of that system and send it to data sinks or time series databases. And this pipeline is now based on open telemetry, which gives us a great ability to send to a wide variety of data sinks. And using this system, we're able to create these dynamic pipelines and both use it operationally and deliver this type of information directly to our customers. Another piece that's important here is that unlike some of the other systems that are out there or have been around in the past, this is sort of a holistic system. It doesn't involve rotating PCAPs or R-syncing things around. There's a control plane that controls all of it. There's a lot of configuration management that you get for free and is available via the REST API. And yes, all of this is free and open source software. So why DNS Insights? Well, so NS1's Anycast network does, of course, have a very unique view of the traffic that's happening for our customers. And the information that's available there is not only of interest to us as DNS operators, but our customers want this information as well, right? They want to be able to debug traffic issues to their applications, to understand if there's misconfiguration somewhere, either on their side or on a vendor's side. They want to understand if they're being attacked in some way. And so they want a very deep view of the traffic that are coming into their domains. Another increasingly important part is the fact that observability is everywhere, right? Likely our customers already have stacks, they already have ways to visualize their application traffic, and they want to see the DNS traffic alongside in dashboards that they build. And so DNS Insights is able to provide the same depth of information that NS1 operators are able to use. So here's a high-level view of the orb architecture. Looks like there's a bunch going on, but we're going to split it up into 3 sections, and then we'll talk about how we used orb for the deployment of DNS Insights. And so on the left side, we have the edge side. So these are where the POPs are. This is where the traffic is coming into the POPs. And so we'll go through the architecture a bit of how we're able to run the agent and analyze the traffic in real time. And we see that this is where these edge queries or these policies come out in real time and tell it what to analyze. And then coming back, we have the OpenTelemetry and the metrics streaming back into the orb control plane. So that's the middle section. So the orb control plane is a microservices architecture that runs in Kubernetes. It's the centralized piece where we have the REST API that you can automate against. There's a UI available. Importantly, of course, this is where all the agents connect into, and that's how we're able to control them. And then on the right side, related to the control plane, we have the sinks, right? So this is where we create our dynamic pipelines, and we're able to send the metrics to their final destination. Okay, so how we built DNS Insights. And a reminder, this is, as free and open source software, this is also a sort of blueprint for how you all could be using the tool yourselves inside of your networks. So we're going to start with the edge side first and talk about how we do the analysis at the edge. So the first thing we need to do is to install the agents so that they're in a position to be able to watch the traffic that's coming into the network. Because we're assuming that we're working with a large fleet of agents, we want this to be an easy process and be a very lightweight process. And so we're using Docker containers for our deployment. There are potentially other ways to deploy it, but we think this is the easiest. This is an example provisioning command that could fire up an orb agent. This is actually something that the UI can generate for you, so you wouldn't have to know this. You can just kind of copy and paste this in. And it's really easy. You just pull the Docker container to install it. It's also the way that you would upgrade is to pull and to restart. And you're able to give it a config file, and surely there's many things that you can customize, but out of the box works pretty intelligently. Another important point is that these agents are egress only. There's nothing that will ever connect into these agents. They only connect out. And we're using MQTT as the protocol, but over TLS, and so the channel is encrypted. So how do we analyze all this traffic in real time? And on the NS1 side, we're analyzing up to something around 1 million QPS. And when I say we're analyzing it, it's not just a sort of one-layered analysis. Because of the policies we'll talk about, there's sort of multiple composable analysis going on across the infrastructure. And so, of course, here it's just a sort of divide and conquer way to do this. This is the first 2 things, of course, will be familiar to any Anycast strategy. So we're Anycasting at the world level into regional POPs. At that scale, either a load balancer or ECMP is dividing up the traffic among the servers. And then we get into the orb specific piece. And so here you can decide to run the orb agent directly on the servers that are running DNS, or you can decide to have a dedicated observability host. And so I'll talk about that in just a moment. And then finally, the next scale is if it's really high traffic and you're processing better than tens or thousands or hundreds of thousands of QPS, and then having a strategy to shard that out on a single server, maybe something to have to look at. And I'll also chat about that in a sec. So we've zoomed into a POP now, and what NS1 has done with DNS Insights is to use a dedicated observability server. One of the big reasons that this makes sense is that it's isolated from faults, right? And if there's a problem with the DNS analysis or the orb agent in some way, it's not going to affect our critical DNS serving. So on the dedicated server that we have set up, we're mirroring traffic at the switch level. And so it's passively viewing all the traffic that's happening across the other DNS servers. And on every observability server, we've installed 2 different orb agents. And again, this is just some fault isolation so that if either we're upgrading the agents or one were to have a problem, we're still analyzing half the traffic. And then we get into splitting out across the resources on the machine and making sure that that happens in an efficient way. And so we played with multiple strategies for doing this. And long story short, empirically, we found that the client source port, the ephemeral port, is actually a good sharding key to split the traffic across the resources on the server. And so we've set up what we call a tap configuration in orb agent to be able to, again, split up that traffic analysis across the CPUs. And don't have time to go into detail on that, but PacketVisor does have an intelligent way to be able to split that up and recombine it to create the metrics and get them out. Happy to talk about that in depth offline. Okay, another challenge we faced here with NS1, right, being an authoritative managed service, is that it's multi-tenant. And so our POPs are serving traffic for all of our clients all at once. And so to be able to do what we want to do, which is to filter and analyze traffic for individual customers, we needed a way to split out that traffic for each customer and analyze it separately and apply the set of custom policies per customer in a separate way. And so in the PacketVisor talk that I gave, I mentioned that PacketVisor supports custom modules, custom loadable modules. And so we've taken advantage of that here and created a module that gets loaded into PacketVisor, which is able to connect to the same database that our DNS server uses to match up the query name with the customer. And that immediately gives us the ability to filter on it. And so for each customer pipeline that we create, we're able to filter the traffic only for individual customers, apply their custom analysis, and get it into their own data pipeline. Okay, so that was the sort of whirlwind tour of the edge side of it. So let's move into the control plane side. And this is where we're going to talk about the centralized pieces, the configuration management side of it. And again, this is the piece that is central, provides the REST API, provides the point for all the agents to connect into over MQTT. And it's also the point you would write automation against. So everything in Orb is API first, and so anything you can do in the system, you can do through the REST API. We do provide a user interface that uses the REST API to make most of the functions easy. So it is call it cloud native app. It's a microservices architecture, and it's meant to be deployed when you're deploying it as a production system into Kubernetes. We do try to make that easy. We provide a Helm chart I'll talk about in a second. As an aside, just because there is a certain barrier to entry to installing it into Kubernetes if you're not familiar with that. If Orb is something that you'd like to investigate and try, we do offer a free SaaS service where we're running the control plane for you. That means that you could install your Orb agents and connect it and try it out without having to run the full control plane. And so that's at orb.live. We know that the system scales to at least tens of thousands of agents. So it's actually based on an IoT framework. And so it's meant to run a very large number of agents together. Based on the resources we've seen while running several thousand agents on it, we believe it'll scale much more than that. It's meant to scale horizontally just fine the more you throw resources at it. It's important to note that Orb control plane does transit the telemetry. It pulls it in from the agents and it sends it to the sinks, but it does not store it, including orb.live, so we don't store the data right now. You do have to give it a sync, and it sends out to the time series databases externally. And we tried to make it secure by default here. So if you do want to install your own control plane, this is our self-hosted install. We've got instructions on how to do it. We try to make it easy. There's a Helm chart provided to help get all the pieces in place. It should work on any Kubernetes platform. We're installing it into AWS ourselves for orb.live and with our NS1 deploy, but it should work on any other cloud system or your own Kubernetes. So what are the types of things that you have to manage in the control plane? So first and foremost, the fleet, right? If you're installing orb agents across your servers, this is where you would provision them and be able to configure them and see heartbeats and make sure they're online and so forth. And so there's a whole fleet management aspect to it. And then we have agent groups. So this is how you group them together, of course, but where that's useful is to be able to address the agents, right? If when you want to send out these dynamic policies we'll talk about, this is how you group them together and say, send this out to this particular group. And of course, one example would be the POP, sending it to a particular region. Here's also where we edit the edge queries, these policies. These are, I'll talk about those in just a second, but that gets edited in the control plane. And relatedly, data sets are how you connect a policy to the sinks, and the sinks are where we send the metrics. So let's talk about the policies for a moment. So these are, policy can be used in a lot of different ways and mean a lot of different things. And so one way to think about them really is like an edge query. So it's a way to specify exactly what you'd like to observe. And so this comes down to filtering and deciding which metrics you'd like to get out of it, right? So if you think of it as like an SQL query, it's going to be something like select XYZ, the metrics you're interested in, where you're only seeing a certain result code, or you're only seeing a certain customer, of course, is important for us in DNS Insights, or where you're seeing a certain AS number or something. And you're able to combine those in a very flexible way to get the exact query you're looking for. And also importantly, to decide which metrics you'd like to pull back, right? If you're not using some metrics, you can decide not to include them in the policy. And so these are all, it's very granular and they're composable. And so the way DNS Insights manages for each customer is to be able to have a policy per customer. We're able to manage the set of policies with a flexible tagging system that's built in. And PacketVisor and Orb handle composing all of the policies together and making sure that it's analyzing the right things. There's nothing special to do there otherwise. And in DNS Insights, right now I think we're giving a sort of a broad traffic policy to each customer. And then we're adding 2 other policies which are a bit more specific and custom according to information that they're interested in viewing. Okay, and then off to the other side of the diagram here, we have the sinks. And so this is where we wind up sending the data to. We did recently complete our move, or just almost completing our final move to an end-to-end open telemetry pipelining system. And if you'd like to check out this project, it's opentelemetry.io. And it's a great system that's really letting us create these dynamic pipelines in a way that connects very well and easily to the broader ecosystem of observability tools. And so to date, we've focused mostly on Prometheus, but with this, we're going to be able to send to both SaaS services and other databases like Elastic or S3 or Splunk and so and what have you. It's also worth noting here that in Orb, the dashboarding and the alerting and taking advantage of the metrics, that is part of the right side here, right? There's no dashboard built into the Orb control plane or alerting. That's expected to happen at the final sync destination. Okay, and so how does DNS Insights manage syncs? Well, one problem we had here was we need to be able to collect the credentials that our NS1 customers have so that the Orb control plane can connect out to them. And so we've added that functionality to the NS1 portal. And so we can collect, for example, the Prometheus credentials that we'll need to be able to send metrics directly to customers. And so on the REST API side, the NS1 REST API can automate against the ORB API and use that to store and automate the way that we control the syncs. And again, because of the way we built the pipelining, we're able to create data pipelines that can take a policy output and send it both to NS1 operational syncs as well as directly to the customer syncs in real time. Okay, that's my tour of the edge and the control plane. Like I said, there is another section in the slides that goes through a bit more about how operators and customers can use the data. And please take a look at that and find me if you have any questions. But key takeaways, so ORB is a network observability platform, and because of where it came from, it's got very good support for large-scale DNS analysis. We've built the NS1's DNS Insights product based on it, which is running at scale and in production today. And this is all free open source software, and it can work for all of you as well. This QR code will take you to the community website, orb.community. And I have a couple other links in the deck as well from some past talks I've given, the orb.live I mentioned, the GitHub page. So that is about all I have. I thank you for your attention. I'll be around. Also, Terry, who's the product manager for DNS Insights, is here as well, and would be happy to talk about it as well. Thank you very much.
Thank you. So people in the room, yes, please, you can walk to the mic. I'm going to start by asking one of the questions that was posted online. James Richard is asking, is your observability server port mirror listening for the DNS over 53? Is DNS tab supported for encrypted traffic that can be read out of the wire? Sorry.
I had a hard time hearing, but is the question, is DNS tab supported?
Yeah, to read encrypted traffic that can't be read off the wire.
Yes, that is now included, and that is the way to read encrypted traffic. So, PacketVisor now supports packet capture analysis, but also DNS tab, and even we moved into things like flow analysis, and it can start to do synthetic analysis and other things. And so PacketVisor is going to grow as an analysis tool, but it does support DNS tab.
Thanks.
Hey, Dan Kriz, Sierra. I'm just wondering, we have several sites where rack space is at a premium, and we don't have the ability to use the span port to port mirror. What kind of resources would the agent use if we're actually to run it directly on the DNS server?
Yeah, it's a good question. On the packet analysis side, we've been trying to spec the analyzer to something like 80,000 to 100,000 packets per second per CPU. Of course, the difference will be the policies that you send it and how much you're telling it to do, right? So if you're doing a lot with it, it's going to be less. But for a basic broad traffic analysis policy, that's what we're trying to keep the packet analysis at. I don't yet have a great answer on the DNS tab side. I actually think that might be a bit more efficient than the packet analyzer, but I think you could expect at least as much as well, 80,000 to 100,000 queries per second per core.
Another question online from Stephen Ubink. Is the PacketVisor multi-tenant module available as open source?
We've considered taking the one that we've created for NS1 and trying to make a generic version of it as an example. We haven't done that, but if anybody's interested in that, we're certainly willing to work with them or to show how to do it, basically, yeah.
No other questions? All right. Thanks a lot.
All right. Thanks for your attention, everybody. Appreciate it.
Welcome back, everybody. So we are going to start session 4 of the first day of DNS-OARC 40. I'm going to go through a small list again of things to keep in mind. During the talks, there is going to be a poll that will come up. Please answer those polls. It helps us better understand, us as program committee, better understand what people think about the different presentations. So I'm Manu. I will be sharing this afternoon again, and we have Willem that is going to be keeping track of time. We would like to thank VeriSign for being the 2023 workshop patron. We are accepting CFPs for lightning talks until tomorrow 11 a.m. They are only open for people which are here on site. What else? Steve Sullivan, which is the OARC membership manager, is outside of the room and is doing presentation. The portal is offering drinks for people taking the quick workshop. So if you go there and check out with him. And I think that's pretty much it. So I will go and start introduce our next speaker. Ralf Weber is going to, from Akamai, is going to tell us about how ready is the global DNS for IPv6.
I haven't done anything yet. Okay, so this talk was inspired by a talk at last OARC from Momaka Yamamoto's. It was a talk about a DNS v6 only resolver. And I said, well, I have lots of data. Maybe I can look into what this is, giving the big picture about this. So we gather large data sets from customers that run recursive resolvers. And we also offer security services. And for that, we have categorization services. So we have multiple partners giving us domains. Say, this domain is whatever, a news site, this domain is nudity porn or whatever. So these are the two data sets I have access to. And then I wanted to look at it, well, if you have these data sets, you don't need to look at each of the FQDNs that you have in these data sets because that would be too much. What you want to know, you want to see the domains that are delegated, so domains that share a certain name server or a certain name server, that is something you can then do a check against. Are they reachable over v4 or v6? Because the reachability of these domains will be the same for all the subdomains or FQDNs within the domain. So this is the methodology. I'm kind of having those large data sets, finding the zone cuts, and then check if they are reachable over v4 and v6. And this is kind of like a slide. We are collecting around 200, 300 billion anonymized DNS queries every day from customers around the world. And then we kind of run that and do a security research with it. And I luckily was allowed to look into that data set also. So that's what I analyzed. Again, it's 300 billion queries. It was 1 week of data, so it was a bit of a reduced set. And then if you do the QPS, because that's what most of the DNS people are interested in, it was around 500K QPS. So after doing the first kind of digestion, because most of these 300 billion queries will be the same, the same top 1,000 or whatever domains. So it came out to 2 billion unique FQDNs. And then I had this other set with 100 million categorized domains. And then I threw that all together. And if you remember, here's the short reminder delegation. So I'm not interested in www.google.com. I'm interested in google.com. I'm also interested in ComNet and the other TLDs to show, how is the query distribution between those. So coming down to the delegated domain, I had 57 millions out of the 2 billion FQDNs. And what kind of struck me, because I was looking at the data, and there were lots of domains there that had a singular hit, or all the domains, all the FQDNs within that domain had a singular hit. So I had the same amount of unique FQDNs as I had of queries. And I then, okay, what is it about that in the total sense? And it's 2 billion out of the 300 billion requests were really unique. And that seems to be an ongoing trend in the DNS, that people use the DNS for all kinds of things, but they don't want to cache stuff. They want to make their uniqueness. They want to find out something, and they want to use it for something else. And so in the end, the domains that really make up the bulk of the queries were 12 million. The others were really, I mean, they also make up a huge chunk, but they were singular hits, and they were probably not as much related to resolution or what people see. I did then the same thing on the domain categorization. Of course, domain categorizations, people are hopefully having better data. So it wasn't kind of the same ratio, but it was kind of 49 million I got out of this. And when I merged these two data sets, I had around 68 million unique domains that had distinct name server sets. And if you kind of put that in perspective, if 300 billion queries are the size of Canada, then the unique FQDNs are the size of Lithuania, and the actual delegated domains are the Comoros down there. So that's kind of like, if you look at large data set, it's, yes, it looks large initially, but it kind of, when you're actually looking at what you're looking for, it comes down. So a word on what I would call one-hit wonders, because that was really, threw me off, because I didn't expect that to be so prevalent. The by far most popular one FQDN hit machine was Google syndication. It's probably ads or something, I have no idea. And gstatic and Google.com are also, I mean, it looks like Google is doing a lot of stuff where they actually signal or do stuff with the DNS. And it's a lot of it. The other stuff was S3 and Amazon. That's probably more expected. If you have an S3 bucket somewhere and you use it, it's probably not as much frequently, so that was not a surprise. What was a surprise was, and this is really out of the top 10, was the Chinese province of Guizhou, kind of how to pronounce that. That had kind of lots of FQDNs. They were kind of singular. And the other stuff, I mean, you expect it, but it looks like for, well, CDN measurement or security people using the DNS as a mechanism to signal something or to kind of maybe exfiltrate, I don't know, is kind of a very common method. And all of them were in the kind of most popular domains. And that's how it looks when you look at it from an FQDN perspective. I mean, they are sometimes random or maybe base 64 encoded or something. They're also what I call word riddles, which is interesting because that's a similar pattern we see in security research where people try to come around pre-registering domains, not based on random prefixes because these are easier to detect, but they use regular words and bound them together so it looks like a real person has done it. But that only makes sense if you do also register these domains. I mean, having that as a prepend for a regular domain, which someone can then turn off, doesn't make much sense to me at least. But it is kind of a common prefix, and this is something probably worth looking into, but again, that was not the initial reason for the talk, so that's kind of a sideshow I heard about. Now, looking to the data, luckily we recently acquired a company called Linode that made it much easier for me to fire up a bunch of instances and then do stuff. Was very handy. And then to discover the zone cuts from the unique FQDN took 2 weeks by that, because I was, it's probably getting faster, but I was just writing some Python code and then making sure finding all the zone cuts on that. I also I wasted probably 10 days because when I've discovered a bug, then I had to rerun the stuff from again. These things happen. And then I did no DNSSEC, no X20, no Q minimization. I wanted to make sure that whatever I do gets me the most positive results into getting to a resolution. Because if I would have turned on DNSSEC or something, I'll probably have a large set that would not resolve or would not find the zone cuts because of validation errors. And then the thing I'm really happy that I made the talk, because the last data gathering finished Friday, so last week Friday, because I didn't anticipate it that, well, I now have only 68 million. It surely must be faster than 2 weeks. Yeah, it was a bit faster. The reason is that you have 3 resolution attempts, so it's actually 3 times the data. But the real reason is failed queries take much longer because there's always then, well, oh, this doesn't work. Maybe let me look here. Oh, it doesn't work. Let me look here. Maybe this works. Maybe this works. It just takes longer. I mean, you can get a positive result in milliseconds, and you have to wait seconds for a negative result. So that's why it took so long. And the other thing is DNS is dynamic. I mean, granted, I started with this work when the holidays started, and that's when I had the data set. So the data set is really mid-December 2022. And when I looked at it, the last kind of queries over the data set were kind of last Friday. And during that time, I mean, nearly 5 million domains, delegated domains that I found via zone cuts were server failed for, I don't know why. And then 2 million no longer existed because they were taken down, or I mean, DNS is dynamic. So overall, we went to 80 millions that we would then have to consider, are they reachable over v4 or v6? Oops, no, that was the wrong direction. Yeah, so these are the results. When you look at the number of domains, 53% are reachable via v4 and v6. And 47% are v4 only, so that's not very good. And there are 337 domains that are reachable over v6 only. So there are some out there. We'll come to them. And I mean, curious-wise, it's a bit better because it looks like popular domains are more v6 ready. So when you look at the amount of queries, and I mean, I knew how much queries they initially kind of had. So I had that number, so I added it up. And the distribution then is you have 68% that are reachable v4 and v6, but 14% that are v4 only. And then again, these small 0% that are v6 only. And when you look at it from the TLD level, I mean, most TLDs support v6. I observed in the data set 1,477 TLDs. I don't know, Ed probably can tell me how many there are on the roots. Okay, so nearly everybody, nearly everything. And then out of these, 23 were IPv4 only. They're on the right. I believe they are mostly CCTLDs because I would think ICANN would kind of come after people that don't do v6 for domains that they delegate. But I mean, the domains are there. And again, the most common in the TLD sector from, again, the number of queries counted up were com.net.org, IO, because that's what all the cool gits do, and HKey. So that's kind of what is looking at the TLDs. Now then, let's look at the sort of what causes IPv6 only failures. And when you look at that dig on the right side, that domain looks okay. It has 2 name servers, and each name server has a v4 and a v6 address. So this should be okay, right? No, it's not. Because the thing you need to keep in mind that when during going over delegation from the root down to your domain, you have to have a v6 record from the parent. And the v6 record from parents are usually, in this case, done via glue records. And if you then have your domain in kind of with all the v6 records set up, but don't have a glue record in your parent, nothing can come to you over v6. So that's very, very important why it's also in bold. You need to add your IPv6 name server to the parent through your registrar. So keep that in mind when doing domains, right? Okay, so let's look at the top 10 IPv4 only domains. Yeah. That was embarrassing when I discovered that. So, yeah, it happens to all of us. Exactly what you expect. I mean, we have a domain called AkaDNS, which is used for I think, GTM most of the time, and it has v6 records, I can tell you, but they're not registered in the parent domain. So I discovered this, I said, last week, and I've opened a ticket with the guys, and they said, what do you want? Oh, it's Super Bowl weekend there, and you're not going to do anything at the moment. So we'll hopefully have it done by the next DNS-OARC. It is really, I mean, But it looks like I'm in good company there, because you see other people like Fastly, or I believe some of them is Microsoft. I mean, so a lot of the big guys also seem to do that problems. And when you think about it, that 86% of the queries still resolve v4 and v6, if these big guys can do something, we can maybe get a bit further. So let's look on the other side, the top 10 IPv6 only domains. And I said, what? Again, some Chinese domain, Taiwan, what's going on there? I mean, they should be reachable over v4. I mean, this looks like a regular domain. So what's going on there? Well, these domains have v4 and v6, so it's good. But what I've seen there, I mean, I've seen it over and over again when doing these testings. I did a talk 2014 about similar things, and when you do testing and you do testing at a high rate of speed, people think you're malicious. So they'll block you. And what was happening there, these domains were totally reachable over v4, but I had done so much questioning over these 100 hosts that they said, nah, we're going to block you. And of course, v6, I mean, nobody does blocking v6. I mean, what's other stuff? So that's the reason why they were v6 only, and there were a couple of them. The other stuff you see there, I mean, are really where people are trying to test v6 only domains, so that's okay. But again, the number was 337 out of 80 million, so it's really not a big deal. So takeaways, DNS is not IPv6 ready. We need to work on that. I mean, CDNs, mea culpa, we need to do better. But given that a lot of the bad stuff that doesn't work yet is CDNs, I'm also seeing a maybe brighter future ahead. And the stuff you need to do when you register your domains, make sure if you have in bailiwick zones that you register the v6 in the parent. And that's it. I'm open for questions.
So for people in the room, please walk to the mic to ask your questions. Otherwise, let's see what we have in the poll. So there is a comment from Victor Duchovny. It is a myth that a large fraction of DNS query will fail DNSSEC validation. I mean, that may be from, will fail DNSSEC validation. The failure rate is south of 1% and is about the same as plain lame delegation. So
that is correct. However, if you look into the long tail, it might still be compared to that a significant number of domains. I mean, it's not probably relevant too much, but I mean, there's a lot of stuff being bad in the long tail. So yeah, that's correct.
I got a clarifying question. In the list you had with some companies you're aware of first, so you mentioned in that case there were IPv6 record at the zone level, but not in the parent, right? Did you do a differentiation between people that were just not v6 at all, like not in the zone, neither at the parent?
No,
Fastly, for
no,
instance,
I didn't do that. I mean, it is probably something worth looking into, but I didn't do that. I mean, just time ran out, but maybe for the idea for a future talk.
Okay.
Sorry, Ralph. Tim Wasinski Cox, DNS co-chair. Glue is not optional, if I can channel Mark Andrews properly. So we're going into working group last call on that tomorrow, Suzanne. So please, everybody speak up on that. But we are strong about that. Glue is not optional.
Yeah, I mean, I'll agree.
Yep, I know you will.
All right, no new questions?
Okay.
So.
Next slide.
So next we will have Roger Murray from Internet Infrastructure Foundation. He's going to present EduDig, making DNS education a little bit easier.
I have no idea what button to push. I owe someone a dance. That was the dance part. Hi, my name's Roger Murray. I've needed one of these mics because I absolutely cannot stand still. I'm from the Swedish Internet Foundation. We do a little bit of DNS. We do top-level domain for .se and .nu. I have no idea what button to push. Okay. We're working on a project called EduDig. Our idea is to make DNS education a little bit easier. I had my emojis didn't come through. They didn't translate. That's an exploding head because I had an idea, and then I found like 5 versions of it online. So that's the way it goes. You have an idea, you think you're an original kind of person, and you're not, or at least I'm not. You might be. Kind of like there's wheels out there. There's different kinds of wheels, but just, they have different uses. So what we're doing is we're not creating a new wheel. We're not even going to make it rounder. We're just going to make a different use for the wheel. And what we're doing is a web dig. And there are web digs out there. I'm pretty sure most of you have seen some kind of web dig tool before. And all of these here have been inspiration. All of these have been used for, it's like I've seen them through the years. This has been done. And I just want to put them in here so everyone knows that we haven't done anything that hasn't been done before. And the idea came from holding a DNS course, and the go-to tool is Dig. But Dig moves. It is not a static tool. The flags disappear, they appear, they're there, they're gone. You get different output sections. And when you try to explain this to people at the same time you're trying to explain DNS to them, you get glaze. People disappear on you. You lose them. So what we wanted to do is, like I said, not a rounder wheel, not new, not original, not revolutionary, I lose track of things. A wheel that's not revolutionary. It's not revolutionary. It's not rounder. This is nothing great. This is a little thing, okay? Oh, Jesus. Okay, I've got a pulse of like 1,433 up here, so those jokes are not going to get caught up. We'll talk about it later over a beer. Speaking to the mic. I was inspired by regex101.com. If you guys haven't seen this site, try it out. It helps with regular expressions and understanding them and showing them to other people. It's a really good site, and it was an inspiration for me for what we're working on. It's EduDig. It's a web-based Dig-ish tool, because it is not Dig. And from the ground up, our idea is to be educational. We want to be able to bring DNS and bring Dig to people that are new to the DNS world. And even in this room, we have 1 or 2 people that are new to the DNS world. Not everyone's been here as long as Lehman has. This is a moving product. It's not a product, it's pre-alpha, it looks completely different already. So this gray has went away, we've got pretty colors now, and we've got something called React, and it's kicking my butt. But what we're gonna do is you're gonna put your query in the top there, and then after you do your Dig-ish, then you'll be able to click on the different flags, and the flags won't disappear, they'll always be there. So the students or the people that are talking about them will be able to reference them. And then you'll be able to click on the flags, and then you'll get the information section over to the right that will tell you about that flag. And it'll give you the information about the different records. It'll tell you about the different query types. It'll tell you about the different flags and their meanings. And maybe if we keep having the ability to develop this, maybe we'll be able to do like, okay, if all these flags are set and not set, what does this mean? And give more of an explanation between that for that. And that's the basic idea. And the reason I'm presenting this so early in this pre-alpha stage, it's going to change all the time. There's no TLS on the website. There's probably no IPv6, sorry, Ralf, is because we want feedback. You guys teach DNS maybe to other people. You guys have a lot of information. If you have any ideas, please get in touch with us. Let us know what we could possibly do to make it better and make it more informational. And just remember that the whole goal is it's going to be informational. Link to the site, and yes, no S, no TLS. And if you go there now, you'll see it looks completely different than the slides I just showed you. It is open source, and drop an issue, drop a ticket, write some code. Contribute if you want, or just heckle me from a distance. That's fine as well. Thank you for your time. And if you have any questions. Aw, the emojis.
Hi, I think this is, sorry, Dave Knight, Ultra DNS. I think that's awesome.
Thank you.
I really like it. One of the things you said right at the top was when you run dig and things come and go.
Yeah.
And so I was kind of expecting in your output at the end that you would have all of the sections and explicitly state, here's the section, but there's nothing in it. I think that would be kind of useful, you know, so that you know explicitly, it's not just missing. It's like, no, this answer didn't have that information, so you should know that it's empty.
Yeah, I understand. Yeah, absolutely. That's a very good input, because then we'd also have more of a static output, and then we could just grade that out. That's very good feedback. And that's the kind of feedback we're looking for, you know, so we can write things in the beginning that make that possible.
Hey, Dan Kriz, Sierra.
Hey, Dan.
So I'm just wondering, you said it's dig-ish and it's not dig.
Yeah.
What are some of the differences in the actual output? That
Dig is a really great tool that smart people wrote, and dig-ish is a really crappy tool in Go that I wrote. And like, I can do 2 flags, and as we all know, dig has all the flags, and then 3 more. And the thing is, I'm really learning things. It's like like dig, you don't have to write out the complete, like you can write plus SHO, and it'll do short for you, but you have to write SHO because there's something else that runs SH something else. So doing some kind of, you know, like auto-completion there. So you know, I'm a big fan of dig, and I'm trying to, you know, get that over, but I realize that when I talk about DNS, when I talk really fast, sorry, is also that, you know, it's like people glaze. But they need to be able to use dig, because just like when Ralf now was showing his presentation, he had 4 slides with dig. You know, so it's something in the DNS community that we need to teach people how to use.
Thanks.
And it's dig-ish because it's not dig.
Yeah.
Cool.
I'm going to squeeze in a remote question first. Patrick Mevzdek asked, do you plan to do like DNSVs giving URLs with timestamp to retrieve the results from the past?
One more time.
Do you plan to do like DNSVs, which is giving URLs with timestamp so you can retrieve result from the past?
I have no plans whatsoever, but drop an issue on the GitHub site, and then I'll have to deal with that. But it's a great idea. I mean, any ideas are acceptable. We're just, you know, in a very early stage, so I'm thankful for all input.
Eddie once said ISC, this is great.
Thank you.
Could you go back to some of your dig-ish results?
I hope so. Yeah, I can. Yeah.
Okay. One thing that drives new students insane is with dig these days, additional will show 1 even when there's not additional sections shown.
Yeah, but dig-ish doesn't do that. It's broke.
That's so
it's broke.
It's broken. Okay. Okay. Good. I was going to ask you to please add it because it drives people insane.
Yeah. Yep. Mats Doofberry is already on me for that, so I think I already have a ticket for that in the list.
Okay.
But
perfect.
yeah, no. The plan is, and if you guys go to the site, and I didn't want to change out the slides because I didn't want Matt or anyone to kill me, but it doesn't look like this at all anymore.
Yeah.
So now it's got more of a React look, and I don't know if we can bring it up. But it's got looks more like a terminal on the left, so it's going to be in black and white, like a terminal should. The information section isn't like my little crappy one because we got a front-end person working on it. It actually sizes after the thing instead of the text just disappearing. And then when you put your query information in the top, the plan is to have a little box to where you can just clip, you know, cut and paste, and then dump that into your terminal. But that doesn't work because I don't have TLS on the site, and you can't cut and paste without TLS on the site.
Okay.
So there's a lot of work to do. So we really appreciate all the input, especially like the one thing. Those are the small details that are important.
Yeah. But overall, I love it, and I love to be able to click on each thing, particularly the flags. So thank you.
Thank you.
I'm going to squeeze another question. So in case your exploding head emoji wasn't big enough, Patrick has another question. Did you look at all the dig clones like Doggo, to get ideas as they try to change the output to make it clearer? So apparently there is other dig-ish or dog-ish tools.
Not really, because one of the primary goals is to make the output to look as much like dig as possible. So we had a workshop internally, and people wanted us to, you know, add stuff into the output and change that around. And that's not the current goal, but at the same time, you know, it's open source, and if people want to add or, you know, come with opinions, we are open to the most. But right now, educational, informational, and as reflective of dig as possible in the output. But nothing says you can't put flat, like highlights on it or information boxes, it says, to make it more informational.
Hi, Ray Bellis, ISC. Quite enjoy this. Want to remind people there is actually also a version of Dig for iOS. You can actually do Dig lookups right on there, and it has really, really stable options because I haven't updated it for 5 years. So.
Tim Wasinski, thanks for this. This is really good.
Thank you.
I wasn't here for Nanog, and I wasn't sure if you were, but one thing I've seen in working with network engineers across multiple companies is they still revert to using NS lookup.
Yeah.
Right? And I still try to say, no, you need to use Dig. And they're like, what's Dig? They're like, it's a little bit of an education with the DNS people, but I think we need to educate network engineers more as to what are the better tools. Uh-oh, Lemon's going to scold me now.
I think what he's saying is you create an NS lookup-ish
no.
tool that
No.
redirects.
I am in total agreement with Tim there. There's like no NS lookup, no hosts, none of that.
Just do redirect.
Just
Hi, Lars Lehmann, NetNode. A couple of suggestions. One, get an HTTPS certificate.
I've got 3 of them. I just can't get them into the Docker container on the right direction. Nginx.
That is a challenge. I'll agree to that. Second one was make it possible to paste a dig command into it, because this will present stuff in a more readable fashion. So you have so you can play around with the various flags to dig and see a better output, or maybe a more consistent output on the page.
Wait, do you want me to be, or do you want to be able to take a dig command and paste that into the? Okay, yeah.
And the reverse, when you have produced this output, at the bottom say this would have been the dig command.
No, we've got that.
You got that? Okay.
Yeah,
fine.
we've got that in the pre-alpha, not in the pre-alpha, but pre-alpha has that. But you can't click on it because I don't have the HTTPS TLS certificate.
Now I have a trickier question. How does this relate to the edudig.eu program?
What, they have one?
Yes, but it's not a dig. It's about digital education.
They've got funding and I've got a hobby.
So you may want to look at finding another name because it may collide in the future.
Excuse me?
Yes.
I'm not that kind of person. Thank you very much for your input.
All right, I guess I got a feedback that I guess I can find online on GitHub, but I think on top of the info section, what would be useful is links to places where you can get more detailed information, like header, how exactly like the Z-Tracks or whatever website that used to have good documentation on how a header look like and what kind of option is there and where and stuff like that. They're kind of tricky usually to Google search them easily, so that may help people to get much more easily into the weeds.
Yeah, and a lot of the information is just taken straight out of the RFCs, and that's not very pedagogical. So we need to look at like better explanations. But before I go into changing, if I take it straight from the RFC, no one's going to argue with me here. But if I start making my own interpretations, then people are going to be on me. So I need to, figure out good explanations for the different things. But absolutely linking to the RFCs, linking to, wiki articles, or, maybe more of an educational wiki for DNS, it might be possible. So thank you.
All right. Nobody else on the queue. We don't have any more questions online. So thanks a lot.
Thank you very much.
All right, so we're closing today. So thanks for the speakers today for presenting good content. Quick reminder, we accept CFPs until for Lightning Talks until 11 tomorrow. For people that are remote, there is a social event happening on the a social space happening on special chat. You should have received all the information in an email. We have a social later for people which are local. It's going to be from 5:30 till 7:30. You need to get there with your badge. You need to have registered and everything. What else? Sorry, I got a bunch of stuff to go through. Yeah, we got COVID test and mask that you can grab outside. I'm not sure how much there is, but if you need some, you can grab them outside. And please, tomorrow, don't be like me. Do your test before you come on site or take a picture. Yeah, thanks VeriSign for being the 2023 workshop patron. And I think we all see each other tomorrow or a bit later around a beer or a soft drink.